Good. So what I'm going to talk about is also connected to work of Bruce, and it's basically motivated or partially motivated by the so-called uniformization problem for metric spaces. So this says the following. So take X, a metric space, and suppose it's homeomorphic to a model space M. For me, this will just be actually, for this talk, a closed and oriented Riemannian N manifold. And the question is, so find conditions, metric conditions on X such that you find a good homeomorphism with good properties from X to M. So one class would be, when is X by Lipschitz homeomorphic to M? But you can replace by Lipschitz homeomorphisms by your favorite class of homeomorphisms. So, for example, quasi-symmetric homeomorphisms and so on. So this problem is still, I think, widely open, and I can't actually say too much about it. I mean, so I don't have new insights. So there are you find relatively easily necessary conditions, which, however, turned out not to be sufficient. So one is that the volume of balls grows like the one balls in M. So this is usually called all-force n regular. So a Hausdorff measure of a ball of radius r is proportional to r to the n. And linear local contractibility, which means that a ball of radius r for sufficiently small r's is contractible in a ball of somewhat larger radius. So a constant times r, and I'll abbreviate this by LLC, even though very often, LLC stands for linearly locally connected, which is related but not the same. So, but for me, this will just always be linearly locally contractible. Okay, but it turns out these are not sufficient, and I'm not quite sure about the literature. Many of you will know much better. So there's examples in dimension bigger or equal to 3, I think by Sems, maybe around 96. And the case of dimension n equals to 2, for me, actually, n will always be bigger or equal to 2. Where the so-called Laxo planes, and Laxo, he showed that there are metric spaces X now, well, homeomorphic to any closed surface that are all-force 2 regular and LLC that don't even embed bi-Lipschitzly in any Hilbert space. Okay, so you have such spaces that are very far from being bi-Lipschitz. And the natural question that you can ask now is, well, if you have a space like this with these properties, what properties does it still share with your model space? Okay, yeah. So of course, properties that should be maybe invariant under bi-Lipschitz homeomorphisms. And a concrete question that I think I learned from Bruce around 2006 or 7 is the following. So suppose X is now, you can ask it for also for others. So homeomorphic to R2, and so suppose it's 2 regular, so all-force 2 regular plus LLC. So the question is then X an absolute Lipschitz retract? Absolute Lipschitz retract. Which means the following. So whenever you have a metric space Y and the subset Z and you have a Lipschitz map into X, can you extend it? So if you have C Lipschitz here by only increasing it by a constant factor. Okay, so that means absolute Lipschitz retract. And so, for example, you can already ask that when this is the circle, for example, or a K-sphere, and here you want to extend it to the K+1 ball. Okay, and by work of Lang and Schlichenmeyer, actually in this case, it suffices to just show that you can extend Lipschitz maps from the circle to the disk and from the sphere to the three ball. Okay, and I believe this question is still widely open and actually quite difficult. And even the simpler question whether you can just extend Lipschitz map from the circle to the two disk is still widely open. Is actually believed to, in general, not be true. Okay, but it's a tricky question because at least Lipschitz curves or Lipschitz circles we can extend in an alpha-Hölder way for every alpha strictly smaller than 1. Okay, so that is maybe an indication that it's not such an easy question. So I would like to turn this question around a little bit. Instead of fixing conditions and asking for a property, I will fix a property that I'm interested in and ask for conditions on the metric space when I still have this. Okay, and the property that I'm interested in this talk is the fundamental class. Okay, so the question is now, when is there an analog of the fundamental class of M in my metric space? And of course, this is motivated by applications we had in mind. So of course, the fundamental class, you can interpret it in many different ways, right? So it is, for example, as a generator of the nth singular homology, or since we are in a Riemannian manifold in M, right, also as a functional on differential forms. So simply by integration. So yeah. So okay, of course we have the same singular homology in X as in M, but of course we want to involve the metric. Okay, so a first naive thought would be to say, well, okay, let's just try to interpret or try to approximate a singular cycle. So the generator of singular homology by a Lipschitz cycle. Okay, so a formal finite sum of Lipschitz map from N simply C. Okay, and as you could already guess, right from here, this we don't know, of course, because we don't know how many Lipschitz maps we have, and actually much more. If we said we don't want to fix properties, so here an easy proposition. So there exists a space homeomorphic to M, so for any M, which is geodesic, which has finite Hausdorff measure, and such that for every Lipschitz map from an open subset of Rn to X has 0 Hausdorff measure in the image. So here, this is open. Sorry, this is, I should write it a bit bigger. So any, Lipschitz map for an open subset, gets really squished to 0. Okay. So this is very important open, because if you replace it, for example, by measurable or by compact, then this is definitely not true. Okay, one can show that for any metric space, basically, you find lots of Lipschitz maps with positive Hausdorff measure from measurable sets. Okay, but it definitely tells you that then you cannot make sense of Lipschitz of Lipschitz chains. So in particular, if you look at the nth homology, Lipschitz homology of X, then this is of course trivial. Okay. But a word of caution, of course, you have very many Lipschitz maps from X to M. Okay, namely every continuous map from X to M can be uniformly approximated by Lipschitz maps. Okay, so in this direction we have a lot. And open question, which is basically just the strengthening of this, asks: does there exist such X, which is furthermore n-regular plus linearly connected, linearly locally contractible? Okay. So such spaces, by a relatively recent result of Guy David, a student of Mario, so these spaces are actually uniformly rectifiable. Okay, so they have big pieces of Lipschitz maps, but they always come from not from open sets, of course. Yeah. So now, well, if we want to interpret it as like a sort of chain, we can't use Lipschitz chains, so we have to have something more flexible. Okay, and this more flexible notion was already mentioned by Urs Lang, and these are the so-called Ambrosio Kirchheim currents. Around 25 years ago, they developed a theory of generalized surfaces, so somehow generalized Lipschitz surfaces. They're actually functionals, which are called integral currents, and which basically works and gives you a very nice and powerful theory in any complete metric space. Okay, so in every dimension you have chains, so-called integral k plus 1 currents. They have a boundary operator, which makes this into a chain complex. And they don't only come with a boundary, but also with a mass measure, so a volume. So any T has a Borel measure. The mass measure of T, which you should think as of volume, the volume measure on your generalized surface. And we call mass of T just the total volume. And moreover, you can also push these forward under Lipschitz maps, like when you have a Lipschitz chain, these induce actually integral currents, and then you can just compose the Lipschitz maps, and that gives you a Lipschitz chain in the new space. And the same thing works with such currents. Okay, so if you have a Lipschitz map between two complete metric spaces, then this induces a push forward homomorphism like this. Okay, and this is a very powerful theory, you know, it's very flexible because, for example, you can also restrict, you know, to subsets. You can restrict your surface or your current to subsets. I will not say anymore. You can think maybe of them as suitable generalization of Lipschitz surfaces over Lipschitz chains, but you have to be careful because in the spaces we're interested in, usually, as we know, there's very few Lipschitz chains, right? 0 Lipschitz chains. Okay, so you have to yeah. But I'll give you soon some applications that don't involve any currents. So if you don't understand or don't know what the current is, it doesn't really matter so much. Okay, so let me state it. I want to say something else. No, okay. So let me state our main result. This is joint work with Giuliano Basso, a former postdoc students, Denis Marti, who is a current PhD student who is also in the audience, and myself. So this is actually work in progress. We start with X homeomorphic to M exactly like this. Suppose it has finite Hausdorff N measure. And so if N is bigger or equal to 3, suppose furthermore that X is linearly locally contractible, and it has lower density, positive lower density at almost every point. So that means if you take the ratio of the Hausdorff measure of R ball with R to the N, then this is positive for almost every point. Then, well, we have this chain complex that gives us homology groups. So I call them the homology groups via integral currents. Then this is infinite cyclic, exactly like the singular homology. And there exists a nice generator, T, a generating cycle. With nice properties which are very close to what you have for this guy here. This actually induces an integral current, except that we don't have differential forms, but Ambrosio Kirchheim, they can make sense of differential forms, which are actually just tuples of Lipschitz functions. So, such that the following holds, that whenever you push forward your cycle under a Lipschitz map, then this is just a topological degree times the fundamental cycle. So for every Lipschitz map from X to M, remember that we have lots of Lipschitz maps, and the mass measure is bounded by a constant that only depends on the dimension times the Hausdorff measure of N. Yes. It's a good question. I don't know. It's true when it's doubling. When it's doubling, then one can do it. And I believe it's a student of yours, right? Kylie Kinberg, who showed that, and I don't know how to do it. So I can do it when the Nagata dimension, when you have finite Nagata dimension, okay? Then the same proof works. Okay, but in general, I don't know. So when it's doubling, it's true, and otherwise, I'm just not sure whether it's true. So, yeah, let me maybe make this remark very quickly. So I wanted to make a few remarks. Oh yeah, so there are of course some previous work. Always motivated by applications, but I don't know too many results. So one that I know is so work of Heinonen and Sullivan from 2002, I think, where they studied the existence of BLD maps from X to Rn, and they're in the setting where you're embedded by Lipschitz Euclidean space, alphas regular and linear locally contractible. They call these cycles Stokes cycles. So you're in Rn, but as we already saw, in general by log, so you cannot embed even into a Hilbert space. Okay. So they have applications that went after with Heinonen and Keith, pushed them further, and then a student of Kai Raila, I think in 16 or in 18, also proved a similar result, so an existence result, which he afterwards used for applications to quasi-regular mappings. Then second, as Mario already asked, so if X is doubling plus LLC, so X in addition doubling, then we have this condition, this lower density. And actually, if so, some results announced by Journey and Jones in 2011, they imply that you actually don't need to assume this condition. Okay, so we only use this condition to apply a deep recent result of David Bate. And for his result, if you combine this with these announced results, then actually don't need to use this ever. But it's likely that already linear local contractibility is sufficient to actually imply this. Okay. Well, so you see in dimension 2, we don't need to assume anything except finite Hausdorff 2 measure. And in the higher dimensions, I'm actually not sure whether we need linear local contractibility, whether it's still true. So it comes in the construction of T, but afterwards it doesn't go anywhere. So it doesn't depend. So this constant only depends on the dimension. So you can actually take Gromov-Hausdorff limits of sequences where the linear local contractibility constant blows up, and in the limit, if this is still has this structure, then you can still somehow pass to a limit for integral currents and get something similar. But at the moment, I'm not sure how to remove this. So now, as I already said, for those who don't know anything about the integral currents, this is of course a bit of a frustrating result because you have the existence of something you don't know what it is, right? So let me give some applications that don't involve any currents. Okay, so the first application is to the so-called Lipschitz volume rigidity problem. So this is the following question. You take X and Y metric spaces. Suppose they have the same Hausdorff, finite Hausdorff n measure. So, and the question is, if phi is a one Lipschitz map, which is surjective, is then phi, so right, phi is one Lipschitz, so it contracts volume, but the volume is the same, right? Does that imply that phi is actually an isometry? Is phi an isometry? So let me maybe give some positive, then some negative examples. So there's no current here, huh? Nothing at all. So it's fairly easy when X and Y are the same. So yes, if Y is the same as X, then, so there you just have to play around with epsilon nets. So if, yes, also if X and Y are closed three-Manin manifolds, and the first proof that I think I know with is by Besson, Courtois-Gallo in their paper on entropy, that's around 95 or 96. And then for the target space that was generalized to target spaces that include Alexandrov spaces, limit RCD spaces, and also so-called integral current spaces. These are spaces that basically support an integral current. So you see that's exactly somehow the setting we are. We have a metric space that supports a nice integral current. And so our we can apply these results. I'll say one word more to get a Lipschitz volume rigidity. And in dimension 2, this recovers a very recent result from maybe a month ago of Damaris Meyer, who's a student of mine, who's at the moment in Stony Brook with Dimitrios and Dalampekos. N equals to 2. That's for like from June 2023. That says if X is as in the previous theorem, let me maybe just give that a name, theorem A. So I'm not a fan of cars, so BMW doesn't mean anything, sorry. It's just like the first letter. If X is as in theorem, oh, sorry, yes, sorry, I should say, let's make it short. Yes, we so have Lipschitz volume rigidity if X is as in theorem A, and Y is a closed oriented Riemannian manifold. Okay, and the proof is just theorem A plus a recent result of Ricci about this Lipschitz volume rigidity of so-called integral current spaces. And so this is just now for us a black box, but I have the feeling this is actually the right setting to prove it. And his proof is very beautiful, and it's inspired by the partial rectifiability theorem for normal currents, okay, where you know that your T gets sent to the fundamental class. So when you restrict it to a function, it gets to a good function, then it gets sent to integration over a BV function. And for BV function, we have like a Lipschitz property on certain subsets, and you use this, and this is the main step, that to show that such a map phi has to actually be locally by Lipschitz. And then yeah, so it's really, I have the feeling with this proof in the setting of currents, this is actually a very natural setting. And of course, their techniques are very, very different from ours. They don't use any currents. So of course, you could also ask about generalizing the target space Y. One can do this a little bit, but you have to be very careful. So just take the standard, say n sphere or 2 sphere, and then instead of taking the n sphere again, you take the n sphere, you take a little geodesic segment, and you shorten this, you know, all the distances on this segment by, say, a factor 1/2. Then the identity map here is 1 Lipschitz. Of course, the Hausdorff measure is the same. It's surjective, but it's not an isometry anymore. So here, generalizing the target spaces, there you have to be careful. Okay, so there are statements in Zust, but I'm not going to go into this. So yeah. Yes, this is a counterexample to this question, exactly, to this question when X is not a Riemannian manifold. Okay. Well, I mean, yeah, so I mean, this defines this thing of an essential length space, where basically, you know, when you take a set of measure 0, and then you can still find curves that realize the distance that don't pass, or yeah, only don't pass too much through this thing. Okay, and exactly this is then excluded, because if you want to go from here to here quickly, it's better to go through here. But this is a measure 0 set, and then yeah, so there is a notion that yeah, but it's a bit more involved. Okay, so the second application is to isoprometric and Poincare inequalities. And this was, in some sense, the starting point of this. And I'm not sure whether I learned this from Bruce or from Kai Raila. I'll comment on this a little bit later. So now suppose X is still homeomorphic to M, and it's n regular So all force n regular plus LLC. Then there exists two constants C and lambda, which only depend on the data, such that we have the following relative isoprometric inequality. So you look at a given Borel set inside the ball, take its Hausdorff measure, or if the complement is smaller, you take the complement. Then this is bounded by a constant times the perimeter of the set in a slightly larger ball. So I'm going to do the perimeter like M for Minkowski content of E in a bigger ball to the same power as the isoprometric inequality in Euclidean space. So to the n, to the n over n minus 1. So for every E Borel, X Borel, and every ball in X. So maybe just a picture. So the bigger ball is here, the smaller ball is here. Here you have your set E. Then this is this set here. And so what is the Minkowski content? Basically what you do is you blow up your set, you take an R neighborhood, and you measure the Hausdorff measure, and then you divide it by R, and you let R go to 0. So the Minkowski content of E in some open set U, this is just the lim inf of the Hausdorff measure of, so the R neighborhood minus the Hausdorff measure of E in U, divided by R, and you let R go to 0. Okay, so you have in some sense the same isoprometric inequality as in Euclidean space. Yeah, and it's well known that such an isoprometric inequality actually implies a so-called Poincare inequality. And so we get a deep theorem back, we can recover a deep theorem of Sem's, which says under the same hypothesis, if you have an n-regular and linearly locally contractible metric n manifold, then X has a weak one Poincare inequality. And as many of you know, the setting of doubling metric spaces supporting a Poincare inequality is in some sense a very good setting on for developing a lot of the first order calculus in the setting of metric spaces. Okay, and so it's desirable to know which metric spaces support a one Poincare inequality, and Sem's result is fundamental in this direction. So his paper is like 150 pages long, so not so easy to read. And actually, in the appendix, he makes a little comment and attributes an idea to Gromov, who says, okay, well, there's actually a potentially easy approach to such a Poincare inequality, which works really well in the smooth setting. And somehow, our theorem here is inspired by this idea of Gromov. And if I have time, I will quickly give a few sketches how we use our current, right? Which, of course, in the smooth setting, you just take the fundamental class as a current. And in our thing, we have this current and how you can use isoprometric inequalities in Banach spaces and properties of area minimizers to give a very easy proof of this theorem, of 5 pages maybe. Yes. Oh, weak because I blow on the right-hand side, I blow up the ball by a constant lambda, yes. So those who don't know what the Poincare inequality is, just look at the poster of the conference, and I think there you'll see actually the 2 Poincare inequality, okay? So I'm not going to use this, so I'm not going to, yeah, but just think it's the right setting for developing a lot of analysis on metric spaces, and you know, these spaces that we're interested in with these properties, they, for example, are very interesting group theory as boundaries of Gromov hyperbolic groups, etc. Yeah. So let me maybe mention just a third application that comes directly out of our theorem. That's so a small application to rectifiability. So if X is again same, homeomorphic to our model space, and suppose it's doubling LLC and finite Hausdorff measure, then X is actually countably n-rectifiable. So that means up to a subset of measure 0, it's the countable union of Lipschitz pieces or bi-Lipschitz pieces of compact subsets of Rn. Okay, and so maybe as a remark, as I already said orally, that if X is the same but is n-regular plus LLC, so again homeomorphic, of course, then we even have that X is uniformly rectifiable, for those who know what that is. And I think this is a result of Guy David. So the American Guy David in around, Guy C. David. Ah, so thanks. Okay, so Guy C. David. Okay, where he uses a lot of the machinery that SEMS developed to get this result, and at least a weaker result we get very easily. What is the thing? So these integral currents, they basically are concentrated on n-rectifiable sets. Okay, so when you have doubling, when you have the LLC condition and doubling, we can show that actually the mass measure of balls is bounded from below by R to the n. Okay, and so then actually so this rectifiable set actually has to be the whole space. Okay, so this follows relatively easily from this. Yeah. So when did I start? Okay, good. So I think I would just like to sketch. Maybe this, because it somehow shows you how you use this existence of integral currents. And if I have a minute left, I'll say something about the first theorem about the existence. So let me maybe, let me just go like this. So as I already said, the main idea or the main strategy of proof is attributed in Sem's paper to Gromov. So proofs. So let's do first the isoperimetric or the relative isoperimetric inequality. And I'll just give an outline how to get a non-relative one. So how I can show the this isoperimetric inequality, which is of course not true, right? So if you have a sphere and you take E very big, almost everything except the cap, then you don't have the isoperimetric inequality. So the perimeter is very small. So this only works if the diameter is sufficiently small. So smaller than a constant, which only depends on the data times the diameter. Okay, and the relative one is quite similar, but just a little bit more involved. So okay, the idea is as follows. So we take our generating cycle, theorem A. And now we have our Borel set E. We blow this up. We take an R neighborhood of E. So then for good chosen R, small enough, well, as I already said, we can restrict our T to such a set. And for almost every R, this actually has still nice boundaries. So it's an integral current. I can take the boundary and I can take the total volume of this. And this is actually bounded by just the perimeter. Okay. This is just called slicing theorem. So yeah. So now what we do is we view X as isometrically embedded in a nice space. Let's call it Y. You can take L infinity or injective hull that Urs already explained. So the nice property of this space here is that since X is compact, E of X is also compact, okay? So with L infinity, you don't have that, but actually it would still work, but yeah. So, and now what we do, we have this, let me draw a picture. I need some new chalk. Here we go. So here, just a schematic picture. This is my X. I have my set E. That's E or ER, right? And now what we're going to do, we interpret this as a current, and then we take a minimal filling in our space Y. Okay, so we take a minimal filling. Oops, such a guy exists, so we can make sense of well, there exists solutions to Plato's problem. So there exists a minimizing filling S of this of this guy here, of this cycle. And well, what we have in this space Y, we have an isochromatic inequality of the same type as in Euclidean space. So the mass of S is bounded by the mass of its boundary to the power n minus 1. The boundaries is just that, and you see, then we get exactly on the right-hand side what we want. Moreover, a very good property of such minimal fillings is that they have a lower bound on the measure of balls whenever this is in the support, and as long as the ball doesn't touch the boundary, so the boundary of the current. So S is in 0 and the distance of Y to the support of the boundary. Okay. So next, so this is already very good. And now the idea is to try to push this current into X. Okay. So currents you can only push forward under Lipschitz maps, and we already saw, you know, in general there are very few Lipschitz maps, right? So we can't push this with a Lipschitz map. So instead we will push it. Well, we'll try to push it with a continuous retraction, which is guaranteed by the LLC condition. So that's B. So there exists a retraction pi from a neighborhood of radius R to X, so continuous with, which has a certain Lipschitz property when one point is in this neighborhood and the other lies on X. So whenever X is in X and Y is in this R neighborhood, and R is actually proportional to the diameter of X. And because our E has a small diameter, so the Hausdorff measure of E is small, so we can always assume that the without loss of generality, that the perimeter is not too big, because if it's big, then it's already true. So without loss of generality, oops, maybe here without loss of generality, we have that the support, the whole current S is actually in this R neighborhood. And now we claim the following, which concludes the proof. So claims. So firstly, E is in the image of the support under this retraction. And the second one is that the Hausdorff n measure of the projection is bounded by the mass up to a constant, of course, by the mass of S. Okay. And once we combine these things, then the Hausdorff measure of E is bounded by the Hausdorff measure of this, which is bounded by this, and by the isoperimetric inequality, we have this, which is bounded by this, and then we're done, right? Okay. So how do we go about proving these claims? So the first one, basically what you do, you take a homeomorphism to your M. Okay. And now you approximate. So you take phi, a Lipschitz approximation of the composition rho pi rho. Okay. So now this is Lipschitz. So if you push, now I push, what do I push forward? I take the cycle S minus T restricted to R. This is a cycle, has no boundary. So when I push it forward, it must be, again, a cycle in M, but every cycle in M is, of course, just a constant multiple of the fundamental class. And because it can't cover the whole of X because the diameter is small, okay? So it has to be 0, okay? So, and this already implies basically this, because, T lives on this set, okay? And then, so if this was not contained in here, then when you push forward, you would also see a current. If the Lipschitz approximation is good enough, it would always, you can show that it actually has support, or yeah, there is a point in the support, and then it's non-zero. So that is this one. And then the second one, you just use this property, this Lipschitz property. So if Y is in the support of S, and I had there, let me see. Here we go. I'll just denote this for the moment by RY. Okay. So then, because of this Lipschitz property, you can say that the image of a ball of radius RY, or proportional to RY, if you want, is in the ball around the projection of the center, and a bigger constant, so actually 3c times RY. Okay. And so now this you just combine with the lower bound, and so you get the Hausdorff n measure of this projection is the Hausdorff measure of this, but this is bounded because it's alphas regular. It's bounded by Ry to the n, and now the radius is so that it doesn't touch the boundary. So we have that this is bounded by the mass measure of this ball. Okay, and now you use a good covering. So this also works if you take proportional. Okay, now you take a good covering which has bounded multiplicity, and all the balls are of radius proportional to the distance. Okay, and from this you get easily then that the Hausdorff measure of pi of the whole support is bounded, and because they have bounded multiplicity, right? If you add them all up, it is bounded by the mass of S. So, and then that's basically the proof. Do I have any more time or? Okay, so in the last 5 minutes, let me just try to show you, at least in a special case, the existence of an integral current. So theorem A, and remember in dimension 2, you have no restriction except a finite Hausdorff measure. So let's maybe do this one for n equals to 2. And for simplicity, I assume that x is quasi-convex. That means any 2 points can be joined by a curve whose length is proportional to the distance. Okay, so how do we go about there? So, okay, by a result of Urs Lang and Martina Jürgensen, we know that surfaces, quasi-convex surfaces, they have Nagata dimension 2. Okay, and then you can use this with some Lipschitz extension techniques that were also developed by Urs and by his student Schlichenmeier. For every k, there exists, well, a finite metric simplicial complex. So that's 2-dimensional simplicial with a metric. And Lipschitz maps psi k, where the Lipschitz constant doesn't depend on k. And a Lipschitz map from the simplicial complex, which is also C Lipschitz, such that, well, the composition is close to the identity. Phi k, psi k, x is smaller or equal to 1 over k for every x. And now the idea is as follows. You have here, you have a homeomorphism. I look at the composition of the 2. Okay, and I can approximate this continuous map by a Lipschitz map. Okay, here I have a fundamental cycle. I can push this forward under Lipschitz maps. That gives me a cycle in here. I push it back with this phi k, and then this, because it's in a small neighborhood around x, this gives me a cycle in a neighborhood, and I try to take a limit, yeah. So maybe just my last. So that's the first step. So B is there exists a Lipschitz approximation. Let's call it eta k from M to sigma k of the composition of this homeomorphism with this Lipschitz map. And of course, the problem is usually when you push forward a current under a Lipschitz map, the mass is bounded by the Lipschitz constant to the dimension times the mass. Okay, and of course we cannot control the Lipschitz constant. Okay, this Lipschitz constant will blow up because, in some sense, we don't have any good Lipschitz maps into this space, right? So this has only a finite Hausdorff measure, so you can forget. You can just take a surface, cut out the hole, put the Pisa tower there. On this Pisa tower, you do more Pisa towers, and if you do the ratios correctly, then in the end you have a fat Cantor set, and you can do that at any place, and you get a surface of finite Hausdorff 2 measure, which is has a purely unrectifiable part of which is dense. Okay, but what we can do is there exists a Lipschitz approximation whose area is bounded. Whose area is bounded by the Hausdorff measure of x. And then you're in the game, right? So then you just take the push forward of the push forward of the fundamental cycle. So that's an integral current in your, sorry, 2-dimensional, of course. It's a cycle with mass bounded by, well, the Lipschitz constant to the power times the area of this guy here. So it's proportional to the Hausdorff 2 measure of x, so independently of the k. So yeah, now we have a sequence of cycles whose supports, are closer and closer to x. So you can just use weak compactness to extract a subsequence that converges weakly to an integral two current, an integral cycle, which is supported in x, and you just have to show that this satisfies all the properties. And so yeah. So in some sense, the hard step is or not the hard step, but the crucial step is here to construct a thing like this. But I think I'm out of time, so I'll just finish here. Thanks very much.
Thank you very much, Stefan. Time for questions. Everyone is eager for coffee. Okay.
In your Lipschitz volume rigidity theorem, what happens when X is not supposed to be a manifold? But can you, of course, it's not true anymore, but can you show that you have an isometry on a big chunk of X?
Okay, I don't know. So the existence result still works under weaker hypothesis, I think. I mean, if you have like a homology manifold and you can make sense of a fundamental class in M or on X, then I think it still works. So there we haven't explored too far yet, and to be honest, the Lipschitz volume rigidity, I mean, is a relatively new subject for me. Only when Dimitrios and Damaris sent me their paper where they do the two-dimensional case, I realized immediately we can do that with our techniques and combining justs. But that's basically when I started to get first thought about this question. So I'm not quite sure. I'm not quite sure.
So what I'm going to talk about is not directly related to what Bruce has been interested in lately, but I decided to give a talk on a topic that should be accessible to graduate students. So try to keep this at the level so that you could not only listen to the first 5 minutes, but to get further in the talk. There are many Italians in our department. They come and go, and I have trouble with people's names, but I've learned how to greet them. So first, if the person's name is Giovanni, then I greet, "Buongiorno, Giovanni." If the person's name is not Giovanni, I know that this is not Giovanni, I greet that person, "Buongiorno, Giuseppe." Because Giuseppe is the second most common male name in Italy. For females, "Buongiorno, Francesca." So I call all the females Francesca. That makes the life easier. Okay. Not at the moment. It used to be rather common in the past. Okay. So let's begin with dimension 1. Very simple setting. So I look at the function which is in W11 locally, and the derivative, distribution derivative is integrable. Then it's locally integrable. The derivative is locally integrable. You can, the standard results tell that it has an absolutely continuous representative. So this absolutely continuous representative necessarily has a limit at infinity. Just use the fact that it's absolutely continuous, estimate the oscillation by the integral of the derivative, right? But you could have a different limit at positive infinity, another limit at negative infinity. So here I'm not assuming that U is in L1, because if I assume that U is in L1, then these limits necessarily have to be 0. Okay? So let's now go to case of P strictly bigger than 1. since I'm not requiring my function to do LP, I can pick up a function that grows towards the infinity and take, like, for example, log, the computer derivative. You can check that the derivative will be in LP when the P is strictly bigger than 1. This means that you don't have limits. So this is the one-dimensional case. What happens if we go to higher dimensions? Turns out that this exponent n is critical. So if I take a function which has a distribution of derivatives in LP of Rn, and the function is itself locally integrable, then this function has a representative which will be absolutely continuous on almost all line segments, especially on almost all line segments, almost all radial line segments towards the infinity, away from the origin, right? So if we go away from the origin, you can think about that your function is absolutely continuous on almost every line. And then what you do, you use polar coordinates and check what does it mean for the gradient to be LP against volume. And you end up getting a weight on your one-dimensional integral. And then what you want is to get an estimate for the integral of the gradient. You get this by using Hölder's inequality. And precisely when P is strictly smaller than n, once you use Hölder's inequality, you end up concluding that you can estimate the L1 integral of the gradient so that you can use the same proof as before to obtain a limit. What is slightly more delicate is that the limit is the same. It doesn't depend on the direction. Okay. The philosophical reason for this is, if you know about Sobolev embeddings, is that when P is smaller than n, you should have an embedding to LP star, but you are not assuming that your function is 0 at infinity. This means that U minus a constant should be in LP star, and that constant is C. Okay? I call this, I say that U has an almost sure limit because you don't have it on all directions, and it's almost sure actually unique limit. Okay? So if you look at the case P bigger or equal to n, this fails. Just take the function log, compute the gradient, and check that the gradient is in all LPs, P bigger or equal to n. This function tends to infinity when x goes to infinity. So this is really a result for, in the subcritical case, P strictly smaller than n. Okay. Here a historical comment. Who was the first one to prove this? So what we do in mathematics, we refer to books. So we refer to a monograph for a fact. And here we wouldn't even refer to anything because we think this is elementary, right? But actually there were papers in Russia. The existence of limits for C1 functions was proven in Russia somewhat a few years after Sobolev introduced his Sobolev spaces. And then the fact that you cannot go to P bigger or equal to n, that was in another paper in a Russian journal. And I didn't put the references here, but actually in the actual paper, I refer to these original works. And we mathematicians, we refer to monographs. This would not be allowed in any other field, right? So what in my opinion we should do, besides citing monographs, we should also cite the original paper, even for things which are trivial in our current knowledge. Because that's one of the reasons why citation counts in mathematics are so low compared to other fields. We don't cite, right? It's convenient to cite the book. We say that, okay, by Federer 3.5.3, right? Okay, so this is the unweighted Euclidean setting. So let me try to now move to a metric setting. So I take an unbounded space so that I can talk about behavior at infinity. And let me assume complete just to make sure that it's sometimes needed, sometimes not. It's a doubling metric space. By doubling, I mean that the measure is a Borel, the mu is a Borel regular measure, which is doubling, which means that the measure of a ball of radius 2 times r is more or equal to constant times the measure of the ball of radius r, independently where the center is located. You have uniform constant for that. And then I assume that we have a Poincare inequality. The Poincare inequality is here. I wrote it in this form. So if you are more familiar with the Poincare inequality where you have p on both sides, that actually follows from this inequality with some work. But this inequality, when one states the inequality like this, you see that this requirement is strongest when p is the smallest. So if you take p equals to 1, on right-hand side, you can use Hölder's inequality and change that to p, right? So in Rn, we could take p equal to 1, and I'm assuming that in my space, I have a Poincare inequality with some fixed exponent p. And one can give examples where you have a Poincare inequality at level p, but not at smaller levels. So one should think that this Poincare inequality is the starting point for the theory. So the role of this p sort of has the role of 1 compared to the classical theory. Okay, and then I need a Sobolev space, and to define my Sobolev space, I'm going to use a version of absolute continuity. And what I require is that there's a control function g. Think this to be the length of your gradient, right? Or think that u is Lipschitz, and this is the pointwise Lipschitz constant. Not the global Lipschitz constant, but the pointwise. And then you require that the oscillation of your function is controlled by the line integral of your control function whenever this makes sense. So what do you need? If the right-hand side is finite, the inequality should hold true. But the inequality is stupid if you get infinity here. So the requirement is that if you have a rectifiable curve along which your control function is integrable, then on this curve, your function is real valued and continuous, even absolutely continuous in the usual sense. Okay? And I use the notation n dot 1p. So the functions are locally integrable, and there's a control function in LP that satisfies this inequality. And this comes from Newtonian, because this is sort of a generalization of the fundamental theorem of calculus. And those of you who have seen the definitions based on density of Lipschitz functions, just if you don't like this definition, take all Lipschitz functions and close them with respect to the norm, where you take the LP norm of the pointwise Lipschitz constant. That will result to the same space as this. There's a small benefit in defining it like this, because now my function is defined in most of the places. A priori, Sobolev functions are only defined almost everywhere. And the trick we do, we take the Lebesgue representative of the function. So we redefine our function as a pointwise limit of integral averages at those points where the limit exists. Here, there's no need to do it anymore. This function itself has the property that the integral averages converge to the value of the function outside a small set. And but sometimes it's convenient to think that our Sobolev functions are all everywhere defined, and there's a trick to do this. Replace u by the lim sup. Lim sup exists at every point, right? And this is the Lebesgue value at the Lebesgue points. And most of the points are Lebesgue points. So I could replace my function here, the N1P dot function, by this kind of a representative. And then I can think that my function is defined at every point. And it turns out that this inequality still holds true. I'm not destroying the inequality. So you can think that our functions are everywhere defined. Okay. Then I need a technical condition which says that we are not on R. If you are on R, take an annulus. The annulus is in two pieces, right? In R2, annulus is in one piece, right? And this is a condition that requires that annuli need not be connected, but almost. So if you look at dyadic annulus, then points in this annulus can be joined by a curve in a larger annulus where you have control on the size of the larger annulus. Actually, if my space is alphas regular and I have a Poincare inequality with p smaller equal to the alphas regularity dimension, this condition follows unless the dimension is 1. So this is sort of a natural assumption from the point of view of the theory. Final comment, I have a 2 here, right? I just put 2 here so that there are some examples, natural examples where you cannot take a ball of the same size on the right-hand side. And this plays no role in the conclusions. Instead of 2, you could put 27 and everything works the same way. Okay. And let me now go to new results in the metric setting. Sylvester was involved in when we did a version of what I'm going to state in the Euclidean AP weighted setting. And Kant Nguyen is a former PhD student of mine. Actually, the smallest PhD student our department has ever had, right? So he bought his clothes from children's section. Josh Klein is Joshua Klein, and he's a doctoral student of Nagesh Shanmugalingams, who visited me me and Sylvester for a couple of months during the spring. So what do I want to do? I look at curves that tend to infinity, because I would like to get limits along along some curves. To simplify, I look at the curves that really go to infinity. There are other versions of this. You could say that the curve goes to infinity if the image contains points outside every ball. Then it would be allowed to oscillate. But for simplicity, let me look at curves that tend to infinity in the sense that the distance to a fixed base point goes to infinity. Or one thing I forgot to say here. So when can we integrate, right? There's an issue. What does an integration mean? You can integrate if your curve is rectifiable, right? And you can integrate if the curve is locally rectified. So when I say that this makes sense, whenever this makes sense, it means that gamma is locally rectifiable curve. And in this case, it means that it's a rectifiable curve because I include the endpoints. Okay. And here's the first result. I'm assuming that I have a P-Poincare inequality, and I have this doubling assumption, some completeness of my space. And the conclusion is that we have limits at infinity, right? For all P. So this is sometimes, the conclusion is sometimes empty, because I just said that in Rn, when P is bigger or equal to n, there are no limits. There are functions that don't have any limit. But I'm saying that nevertheless, there's a finite value C, so that the limit at infinity x equals C along P almost every curve. So the catch must be in this, what it means to have P almost every curve. Okay, and the definition of P almost every is cooked up basically from modulus of curve families. So P almost every means that there's some subfamily inside these curves that go to infinity, which is small. And for all curves which are not in the small family, things work out. And then I will have to define what it means to be small. A family is small in the sense of P if for any positive epsilon, I can put a weight, I can find a weight function so that the line integral over my curve is at least 1. So with respect to this weight, the curve has length bigger or equal to 1. And then what I do, I look at the LP norm of this weight function and try to minimize it. Okay? Abstract nonsense, right? So the next issue is how is this related to the Euclidean case? In the Euclidean case, it has to be the case that P modulus of the family, family of gamma infinity is 0 when P is bigger or equal to n, because I don't have any limits. So this means that my small gamma here, which is a small set inside gamma infinity, is actually gamma infinity. Okay. So why does this hold? That's because of volume growth at infinity. And I have a doubling space, so I don't have a dimension a priori for it. So I try to cook up something, a condition which is like isoperimetric profile in a certain sense. So I look at how the volume grows at infinity. So I take the sum over the dyadic levels. I look at the measure of the dyadic annulus, and I raise the measure to power 1 over 1 minus P. That's a negative power when P is strictly bigger than 1. And I sum that against a positive power of 2 to the j. Right? So this becomes small if the volume grows really fast. That's the philosophy. Okay. And when P is 1, I just directly compare the measure of the annulus to the radius of the annulus. And here is the explanation why things work in Rn. There are some curves left precisely when this Rp is finite, right? So the whole issue is about volume growth at infinity. And it turns out that this is equivalent with the requirement that every function in my Sobolev space has at least one limit at infinity. There's at least one curve along which you have a limit, right? And how can this be equivalent? That's because the point is that I say for every, right? That's similar to what Asaf was telling in his talk, that if you put a condition for all functions or all sets in your collection, then it becomes a strong one. Okay. So then the next issue is, could I do better, right? Now I know that there should be curves along which I can have a limit. Could I prove that there are a lot of them? Now let's think about, what am I assuming? I'm assuming a Poincare inequality, doubling, then this annulus condition. R plus satisfies this. How many curves to infinity do I have in R plus? Modular parametrization or killing loops, only one, right? So in some sense, this is the best you can say in this general. But I would nevertheless like to get a conclusion which says that for almost every direction, right? On R plus, I can say that for almost every direction because there's only one direction. And for that, I have something, right? So to do almost every direction, I need to have some kind of indexing for my curves. And towards this, we try to define polar coordinates abstractly in a form that would be suitable for what we are doing. So what are polar coordinates? Polar coordinates come with an index set. That's like the set of directions. Then you have curves indexed by your index set. So I look at curves going to infinity, and they are indexed by xi, which is in some abstract set S. And I require that that they start from a fixed point, and then I require that there's a probability measure on S, so that I can talk about almost every. And then, what does the polar coordinate mean? It means that if you integrate over curves and integrate over the index set, you should not get more than the actual integral of your function, right? So there's this magic function h here that has the role of R in classical polar coordinates. Now, do we have examples? Let me draw you an example to show what. So this space is not doubling, but I just draw this to show you what is going on. Yeah. Good point. Let me explain this. H is non-negative at this point. Okay. So look at this space. Let me make this my base point. And now I have this family of curves going to infinity. And my parameter space is this line segment, this circular arc. Where do I put my h? I put the h on this side, not on that side, because my curves do not occupy this part of my space, right? So I'm not requiring that h is strictly positive. I'm requiring that the inequality holds. But I know what your point is. This is always true. Just take h equal to 0, right? So the interesting case is where you can find an h which is not identically 0, right? And if you look at this space, on the right-hand side, this is like usual polar coordinates. So here you should take h of x equals mod x, right? On the left-hand side, I could do the similar thing. I could start with curves going first to this line segment, and then continue in a parallel way. And now if you think about your polar coordinate h, what should you put? 1, right? So on this side, you would have h1 equals 1, identically 1, right? But there are many other choices. On the right-hand side, away from the origin, I could take square root of mod x. That works as well, because I'm not asking this to be equality. I'm just asking that this is smaller or equal. And from my point of view, I don't care what happens here, because I'm interested in what happens far away. So what I want to assume is that a negative power of h is integrable in the set which consists of the images of my curves. So I want to assume that h is strictly positive in the union of the images of my curves, almost everywhere, right? And since I'm interested in what happens at infinity, I don't care what happens close to the base point. So I put a condition which measures how close to 0 h is far away. Now, in Rn, what is your usual polar coordinate? That's t to the n minus 1. So this would be t to the n minus 1 to p over 1 minus p, and then you compute and check that how things work, right? And then what I wrote here is just that I'm really interested in what happens far away. No, I don't care what happens close to the base point. Okay. So now there are two things I want. One is that there should be at least one curve along which I have a limit. But I would also want to know, do I have limits along almost every curve? And now, once I have my polar coordinates, I can talk about almost every curve. And the conclusion is that this integrability condition on the negative power of h is sufficient to have limits along almost all curves. On the other hand, the volume growth condition is necessary. So the truth is somewhere in between, right? So you cannot do anything if the volume growth at infinity is bad. You can do things if there's a nice foliation by curves so that the curves do not overlap too badly and they spread out nicely. That's what this is saying. And there's notice that my first condition doesn't say that there exists the limit. I'm just saying that every function remains bounded along some curve to infinity. That implies so necessary condition for that is RP being finite. So actually it turns out that RP being finite is equivalent with the first statement. But in order to get almost every direction, I need something to measure the directions. Okay, there are more different versions of the statement, but I tried to give the simplest possible one. So as the last thing, let's look at the case p bigger or equal to n more carefully. Turns out that you can make bounded counterexamples. My counterexample was something the way the function increased to infinity, but you can cook up in Rn functions that oscillate so that there's no curve towards the infinity along which you have a limit. The situation is somewhat different when we are at the level of the dimension. To talk about the level of the dimension, I'm assuming that my space is R-force regular. So the measure of every ball is comparable to radius to a power q. And then the conclusion is that if I'm given a function, correct. So once I talk about the Sobolev space, I'm assuming that I have a Poincare inequality at the level of my Sobolev space, right? So remember, there was a counterexample. There are bounded counterexamples in Rn. So being bounded doesn't guarantee yet anything. What I'm saying is that if there's a curve along which you have a limit, then there are a lot of curves along which you have the same limit. No polar coordinates in this statement. It's just telling that, okay, there's a collection of curves going to infinity so that they are not too long. They do not oscillate too much. And the union covers most of the mass, a big portion of the mass towards the infinity. So the case P equals Q is somehow very strong. If you have a limit, then something nice happens. This is not true if I take an exponent which is strictly bigger than the dimension. So what you could have is that you have different behavior in different directions. It's really that I'm in the borderline case. Yeah, yeah. C is basically the limit of integral averages of your function over spheres. So look at the boundary of a sphere, take the integral average over that and push that to infinity. Turns out that that's the value. It's sort of the average value of your function integrated against all the directions. That's not immediate. And another way to say in the Euclidean setting is to what I said earlier. Once you are below the dimension, then the limits exist, and the limit is basically the constant that makes you have to subtract from U so that U becomes an LP star function. Okay, so in the case P equals Q, we have rather nice conclusion. Go ahead. Oh yeah, sorry, this should be 2 to the J. Yeah, R should be 2 to the J. Yeah. So it's saying that the measure of the annulus is full, basically, modular constant. Thank you. That's a typo. So it should be that the measure of this set is basically the measure of the annulus. And then the final thing, what about almost every? I have these polar coordinates. Can I use my polar coordinates to conclude that if I have, in the case P equals Q, can I conclude that if I have a limit along one curve, then I get the limit along almost every curve? To do this, I should have some condition on my polar coordinates. The earlier conditions I gave fail when P is equal to Q in Rn. So that's not the condition I want. The correct condition is that my curves spread out nicely. So if I look at far away and look at the projection of my curves to the base points, this projection should be Lipschitz, and the Lipschitz constant should go to 0 when I go to infinity. Thinking it in Rn, if you have two different directions, the distance between points on these two curves grows linearly, right? So this is the similar requirement telling that if you project towards the index set in the abstract sense, then what you end up getting is something that shrinks a lot. Under this condition, you can conclude that you have something for almost every, assuming that your measure on your index set is absolutely continuous with respect to some Hausdorff measure. And you have to assume this because you could have atoms, for example. So you have to somehow relate the measure to what happens far away. And the Sobolev space theory allows you to really relate things to Hausdorff measures living on your space. But the measure sigma lives on S, and a priori has nothing to do with the rest of X. So you have to put some condition, and it turns out that this kind of Lipschitz shrinking phenomena does the job. So the conclusion is that if I have spreading polar coordinates, then if I have a function in W1Q or N1Q, a gradient in LQ, and I have a Q Poincaré inequality, and my space is alpha Q regular, then I have a lot of limits. And this is the last slide. So I started from the Euclidean setting. My first conclusion was that you have limits in almost all directions if P is strictly smaller than N. This is telling that also when P is equal to N, if I have a limit along one line, then I have the same limit along almost every line, almost every direction. Okay, so this rounds up the thing. There's still some things of the case P strictly bigger than N that I didn't pick. P strictly bigger than the Q, then I don't want to go do this. But now that this is done, what next? what happens in the homogeneous case? I look at non-homogeneous case. My results are for the homogeneous Sobolev space. What happens if I additionally assume that my function is also in LP? Okay, what happens in Rn? Take a function in LP which has a gradient in LP. Does it have a limit at infinity? If it has, the limit has to be 0, right? Turns out, yes. P plays no role. So in Rn, if you take a function in the non-homogeneous Sobolev space, it has the radial limit 0 for almost every direction. So this means that perhaps there's a metric counterpart of this. And this is something I've been discussing with my postdoc, Kaushik Mohanta, who's sitting here. And it turns out to be complicated, right? So at the moment, I have no conjecture what the correct condition should be. It seems that things work extremely nicely in this homogeneous case, which somehow is natural because our definition of the Sobolev space is based on the oscillation of your function, oscillation estimates in terms of the gradient. The LP part in even the classical Sobolev space, no, it's somehow it's put there so that you get the LP function, but it's not involved in the estimates. So it's typically easier to do things in the homogeneous case than in the non-homogeneous case. And that's the only explanation I have for not being, only excuse I have for not being able to do the non-homogeneous setting. I don't even know what the statement should be. Okay, that's all I wanted to say. Thank you.
Thank you. Any questions?
Hey, so do you have some criteria under which you can construct this gamma, naught, S, and sigma, other than, well, when you're in some, well-known or smooth situation or something?
I have no theory. We have examples, but no real theory which would allow us to say that, okay, suppose you have a space in this category, then you can build this up. And the issue is really pinching when you start to think about it. If even under Poincare inequality, your space can be pinched in some places. In the place where you have pinching, H has to go to 0, right? Because the curves overlap a lot. And that makes it complicated. So I'm having a student to try to construct, I'm sure that this works out, construct a space where you're sort of pinching through a Cantor set infinitely many times towards the infinity. And nevertheless, you can get reasonable polar coordinates. I think this is possible to do, but that's still very experimental. So I don't know. That's actually what I once tried to ask Sylvester. Could there be some general theory? Suppose you have a Poincare inequality. Does it follow that you have something like it? What is the best type of polar coordinates you can construct simply by assuming Alford's regularity and a Poincare inequality? I don't believe that you can do a lot, but at least one should be able to show what is the best one can do without putting curvature conditions. So I think you have to put some kind of a curvature condition for your space in order to get a nice polar coordinate.
All right, thanks.
Well, maybe I'll continue on this then. So the same space, of course, can support many polar coordinates.
Yes.
It's not exactly unique or canonical, but would there be some choices that would be more natural than others? I mean, it's related to the comment that you just made, and I'll give one example. Say gradient curves of Green's functions, anticipating the talk tomorrow a little bit, but
yeah, that sounds like a very good. I mean, one should build up a procedure to construct these coordinates so that once you start with your space, you look at the properties of something on your space, and that gives you this level line. So whatever they should be called. So this is what we have done, in my opinion, is sort of a naive attempt to single out what makes things to click. If you can prove something like this, then things work out nicely. The next issue is, can you ever prove that this kind of things exist? Yes. So I set up the definition so that you always have polar coordinates, right? Now the issue is, can you have non-trivial polar coordinates? That's the real question here. You always have a polar coordinate. Just take h identically 0. And sometimes you have to take h identically 0. For example, suppose the image family of your curves has volume 0. Then the right-hand side in your equation is 0. This means that the only h you can really put in there has to be 0. Yeah. Yeah. No. So this h plays no role here in this conclusion. So this is about how the geodesic spread. So in this sense, you can take h to be 0 for this theorem. This theorem doesn't rely on h.
So in the case of the curve gamma x naught c, is not this a part of a system of polar coordinates? Is not this?
Yeah, but what I'm saying is that I just use the same terminology. Take a polar coordinate, don't care what h is. If the curve spread out, then 1 and 2 are equivalent.
Oh, okay.
So it's just saying that if you can find a nice family of curves going to infinity so that they spread out nicely,
Yeah, okay.
then these two conditions are equivalent.
Thank you.
Okay, so our next speaker will be Elefterios Soultanis from the University of Warwick, and he'll tell us about curve fragment-wise differentiation of Lipschitz function on metric spaces.
Thank you very much. I'd like to thank the organizers for the invitation. It's a great privilege for me to be given the chance to give a talk here and celebrate the mathematical contributions and legacy of Bruce Kleiner, which, as we've seen, spans a vast number of fields. What I will talk about is happening in the setting of metric measure spaces. And well, Pekka Koskela just now already talked about something in this setting, specifically with the PI spaces. Whoops. So that's what I will start with to sort of review, and then I'll go on to talk about the central topic of this talk, fragment-wise differentiability, and time permitting, tell you something about the proof. So this story starts with Cheeger's Rademacher theorem from his seminal paper from '99, which says that when you have a PI space, then you can cover it by countably many charts, which are called sometimes Cheeger charts or Lipschitz differentiability charts, that are characterized by this property that every Lipschitz map admits a unique differential with respect to the chart. So the chart is a pair where U is a Borel set and phi is a Lipschitz map into some Rn, right? Yeah. And well, Pekka already spoke at some length about this PI spaces or Poincare inequality. I'm just recapping here a way to write it. And here's another way to write it, where instead of the pointwise Lipschitz constant, you have the minimal p-weak upper gradient. So what is that? We saw what an upper gradient is. So here I'm suppressing some of the details that Pekka addressed, namely, what does this like how do you interpret this when one side is infinity and so on. And also I'm just looking at Lipschitz curves because you can parameterize rectifiable curves to be Lipschitz. And the upper gradient simply tells you that you have control of the oscillation of the function along the curve, along all curves, by this line integral of the upper gradient. So fixing a function f among all of its upper gradients, it's not necessarily true that there exists a minimal one. So you cannot take a min or an infimum of these and hope to get an upper gradient. But you can if you relax this condition a little bit by allowing or requiring this condition only up to sets of p modulus 0, so a negligible set. So you throw away a negligible set, and in this sense of the modulus, so here I write the definition of the modulus. It's, as Pekka said, some kind of abstract nonsense, but it gives you a notion of negligible families of negligible sets, negligible families, yeah. When you weaken this condition, so you only require this outside a null family of curves, you do have minimal, there exists a minimal p-weak upper gradient, as it's called. And I write here this notation that I will sometimes have to indicate that in general this object, it depends on p. So when you change your p, you change the negligible family. This can result in a different thing. Okay, so just a quick list of consequences of PI for PI spaces. So one, which is due to Cheeger, is that the Sobolev space is reflexive. Then you have the Sobolev and Nirenberg-Mori embeddings and Rayleigh-Kondrakov compactness theorem due to Heiwash and Koskela. You have this Cheeger's Rademacher theorem, so Lipschitz functions are almost everywhere differentiable. And here is also something that Cheeger and Kleiner did in 2009, that a stronger version of this, where Lipschitz functions into certain class of Banach spaces, so those having the Radon-Nikodym property that I'm not going to define here. So Lipschitz functions into these are also almost everywhere differentiable. And turns out this is strictly stronger, in fact, than just real valued functions being almost everywhere differentiable. And so this is just a very short, non-exhaustive list of consequences, right? And we saw one in the previous talk, another consequence in the previous talk. But here I single out, for the purposes of this talk, a theorem where, so this part here is due to Cheeger, and this slightly informally formulated thing is due to Cheeger and Kleiner from this same paper. And I'm thinking of this rightmost equality as a representation of the minimal weak upper gradient. And well, this is an equality. And a remark is, so this is not something that's obvious, but it's kind of the philosophy of what I was doing, what we were doing. So this representation, so this guy, plus this fact, that this equality, can be used to kind of construct the differentiable structure when you have a PI space, or then more generally, whenever you have these two things, you can construct the differentiable structure. So maybe I should say one thing. So some of these things in this list are generic, more generic than others. So for example, this turns out to be true without the assumption of PI. For example, when X is doubling, this is due to, I think, Ambrosio, Di Marino, Savare or Gigli. And also when the X has finite Hausdorff dimension. So it's a very general fact in a way. These do heavily rely on the PI, and they're not true without it. These, at least the embeddings. So this RMP valued differentiability is not quite the same thing as a Poincare inequality, but it's kind of close in a I guess quantitative infinitesimal sense, and due to work of David Bate and Eriksson Bick. This, however, is also not as generic as this, so it's not true for as wide a family of spaces as this is true for, but it's more generic. It's a weaker condition, and that takes us to Lipschitz differentiability spaces, which, so here I list a very, again, non-exhaustive list of authors who've contributed to this topic. This has been widely studied by now, and so Lipschitz differentiability space is basically a space where the conclusion of the Rademacher theorem holds, so that you have charge with respect to which all Lipschitz functions are differentiable, right? So that's just the definition. Again, a short list of properties of these things. So in fact, so here I'm already dropping any doubling assumption from the measure. So for PI spaces, usually you say that they support the weak Poincare inequality and the measure is doubling, and that is PI. Here you don't assume a doubling condition, but it in fact follows from being an LDS, as I'll abbreviate it, that, so it doesn't have to be doubling, but in an infinitesimal sense it is. So it's pointwise doubling in the sense that the lim sup of the ratios, the volumes of balls, is finite almost everywhere, and this is due to Beit and Speit. And unlike PI spaces, this class is in general not closed under measured pointed Gromov-Hausdorff convergence or anything. So therefore this is, I don't know if it's surprising, but it's definitely not a trivial conclusion or anything, but it's true that a tangent of an LDS is also an LDS. However, so these spaces don't need to be rectifiable, and as an example, you can think of the Heisenberg group or just Carnot groups. And again, unlike PI spaces, LDSs don't need to contain a lot of curves. They don't need to contain any non-trivial curves, actually. And they, don't need to have even this sort of infinitesimal version of the Poincare inequality. So this can be thought of as an infinitesimal version of the Poincare inequality, but they don't need to satisfy this. Okay. So the moral when studying or analyzing LDSs is that curve fragments replace the role of curves. And so what is a curve fragment? I suppose the name sort of gives an intuitive idea of what it should be. And here is the definition. So it's a bi-Lipschitz map from a compact set of the real line into the space. And the kind of main difference with curves is that now you don't assume that there's a connected set. So it doesn't need to be an interval. If you put fit the smallest interval that contains the domain, and you look at the complement of the domain there, because this is a compact set, the difference is a countable union of open sets that may or may not include these. No, it does not include these, I guess. Anyway, we just kind of, to set some notation, define the gap of gamma of a curve fragment to be just the sum of the gaps, informally speaking. And this is, of course, going to be some finite number because this curve is a bi-Lipschitz, so it will have sort of finite length. All right, so curves are examples of curve fragments, obviously, except for the fact that, okay, here we have a bi-Lipschitz, right? And we don't usually require curves to be bi-Lipschitz, but modulo this sort of detail, curves are curve fragments with connected domain. And in a way, what will be most relevant for us is when the domain, so here you can also have domain can be 2 points, 3 points, or something like this, a discrete set, or even a Cantor set with zero measure. But in a way, those won't affect what this talk is about so much, because of the fact that their domains are negligible in the sense of the measure. And so the most relevant case for us is when the domain is a fat Cantor set, usually. But this will not explicitly appear really in this talk. And here, just to set up some notation, the set of curve fragments is denoted by FR. And then another thing here, I just put a bar above to denote the set of pairs where you have a curve fragment and a time parameter that is in the domain of the curve fragment. All right, any questions so far? I guess this should still be okay. And specifically the way that these curve fragments appear is through what is known as Alberti representations that I think was defined by Bate and Lee. I'm not entirely sure, but based on ideas of Alberti. They are kind of decomposition of the measure into curve fragments. So here's the formal definition. Let me just see if I can tell you what you should be thinking of here is the Lebesgue measure on the plane, say, admits such a thing, admits two such things, in fact. So by the Fubini theorem, you can sort of take this family of curves that are also curve fragments now, and the Fubini theorem tells you that this sort of identity is true. So foliating the square by these lines in either in the vertical or horizontal direction gives you two Alberti representations of the Lebesgue measure restricted to the square, say. So just to give you an idea of what this thing means. But formally, you have this probability measure on the space of curves or curve fragments, and then these collections that decompose the measure. So what does this have to do with LDS? So here's a first proposition. I don't know, I guess it's due to Bate, but it's not something that's very, it's not super deep. The deep theorem is in the next slide. But when you have an n-dimensional LDS chart, so the dimension here refers to the dimension of the target of phi. So phi goes into Rn. So if you have an n-dimensional chart, then the restriction of the measure to the chart admits n Alberti representations which are phi independent. So what this means is that after mapping almost every curve with respect to this pi, they point with phi into the Rn, they point in independent directions. So think here of these two Alberti representations given like this and like this. And here you see that they are concentrated on independent directions. So that's, again, the intuitive picture you should have. Okay, so this independence of Alberti representations is like an important piece in this theory. But it's not quite enough to characterize Lipschitz differentiability charts. Here I don't really want to go into this too much. But there's a stronger notion called universality of a collection of Alberti representations, which is given here. So basically, the collection has to sort of simultaneously see all the possible directions that any given Lipschitz map can grow in. So that's a technical definition, and the deep theorem due to Bate is that the existence of these actually is what characterizes Lipschitz differentiability spaces. So space is a Lipschitz differentiability space if and only if you can decompose into these sort of charts which admit such a thing. So they admit n phi independent Alberti representations, but they're not just phi independent, they have this universality property. And as a kind of corollary from this, you again get this sort of representation, which is now even more informally written. So I take that some kind of essential supremum, because of course, I mean, none of these quantities need exist just for any curve fragment, but suitably interpreted, you have that the point-wise Lipschitz constant is comparable at least to this sort of maximal directional derivative, if you want. Okay, so this brings us to fragment-wise differentiability. So what happens when you don't have these universal collections of Alberti representations? Well, you can still talk, you can still define notions of differentiability, as we'll see. And the heuristic is that whenever you have this minimal object, so the minimal p-weak upper gradient or some other kind of minimal something upper gradient, when you have a representation of it as a maximal directional derivative, such as we saw in the theorem of Cheeger-Kleiner, or this corollary from the result of Bate, so that gives rise to a weak differentiable structure. And so here's a concrete example of that. So with Sylvester, we did this for the minimal p-weak upper gradient. And so I don't give you the representation, but instead I give the conclusion that we drew using that thing. So it is that, so given a p at least 1 and a metric measure space that has just finite dimension. So by the way, I assume that X is, or the metric is complete, and I assume that mu is a Radon measure that is finite on bounded sets, just to keep things neat, but still these are very general assumptions, of course, much weaker than PI or LDS or anything like this. So such a general space, whenever it has finite dimension, it admits a p-weak differentiable structure, as we call it, which means that it can be covered by a countable number of p-weak charts, and the charts will have dimension at most Hausdorff dimension. And what is a p-weak chart here? It's again, it's characterized by admitting in this case, every Sobolev function admitting a unique differential. But here we have to interpret the differential in a curve-wise sense. So in this generality, of course, it's hopeless to hope to have any kind of a total differential. But for mod p, almost every curve, you do have this at almost every point where the curve is inside the chart. So what I want to do is take this heuristic and apply it in this, so not for this Sobolev space case, but more closer to this world of LDS, so where you have curve fragments. And to do that, I just introduce a minimal object controlling curve fragment-wise behavior. So this is the curve fragment analog of what an upper gradient is, which what it says is that the oscillation of the function along the curve is controlled again by the line integral. But here, so I mean, this is the same thing as integrating rho. I mean, the rho gamma t speed of t dt over the domain, but the domain now can be a fat Cantor set, say, and so you cannot hope this term alone to control that. But you add this gap term. So this controls on the parts that the path of the curve fragment really sees. This rho controls the oscillation, and in the gaps you just use the global Lipschitz constant. And in particular, this thing as it stands here is only defined for Lipschitz functions. It's not defined for any kind of function. Yep. Well, I am measuring them in the space. There are other conventions as well where, but for me, I found it, most convenient to measure them in the space. And now, so there the content is that there are no Sobolev functions, no non-trivial. Well, no. The Sobolev space is trivial, which means that all LP functions are Sobolev functions. So what happens there is that the p modulus of all the p modulus of all rectifiable curves is 0, and so the conclusion here is empty. Yeah. So in other words, you can say that there is a trivial chart. So the chart is of dimension 0. And of course, this is something that one has to accept in this generality. It certainly can happen that the dimension of the chart is 0. That means that part, at least that part of the space, supports there's nothing non-trivial going on in terms of Sobolev functions in this case. Okay, so we have the notion of what we call star upper gradient. I think also was introduced by Bate and Lee. And similarly, we can, so this does not need to have, there does not need to exist a minimal guy like this, but after relaxing this condition by now the infinity modulus, there is a minimal infinity weak star upper gradient that I'll denote like this. And here the infinity modulus is kind of formally the same or similar as the LP modulus. So it's just notable differences here. Note you are integrating only over the fragment, not any full curve. And so in particular, you're not adding this gap term here for this admissibility condition. You don't want to do that. And there are significant differences caused by the fact that you take the L infinity norm here that I will also kind of hide under the carpet in this talk. And well, just a comment, the infinity modulus is the strictest modulus, so it's most difficult to be null with respect to that modulus. So if you are null with that, then you are null with respect to any finite p. And you have these inequalities that are sort of easy to see, or elementary enough, and they can all be strict in general. And so here's the representation theorem. So for any Lipschitz function, there are probability measures on the space of curve fragments paired with the time parameters, so this fr bar, for almost every point where this minimal guy is positive. So each of these p x's, p bar x's is concentrated on this set, on the set where the curve at time t is x, so that you have this representation. So here, this is just a way to talk about generic. Now instead of phrasing it informally, I phrased it more formally by saying that what I mean by generic is in the sense of this measure. And so I won't say anything about the proof of this, except for that it has these two ingredients: plan modulus duality that works well for finite p, and this is the statement, but it's not so important. For infinite p, this doesn't work as is written here, and there are some difficulties that we have to use a weaker version of this that is still sufficient for us. And then the second ingredient is this disintegration, or a generalized Fubini theorem, if you want. So this is again sort of very abstract. I wrote it in great generality, but it's a way to disintegrate the measure into slices. What I forgot to write here is that each of these should be concentrated on the fiber of E. That is the same set as here. This is the fiber of E at X. Okay, so you maybe see the notation is similar. So somehow the measures come from this once we apply this modulus duality. But that's all I want to say about the proof of the representation. And I'll spend the remaining few minutes trying to tell you what the fragment-wise differentiable structure is. Well, so here's the theorem whose proof uses that representation, is that whenever you have finite Hausdorff dimension, then you can cover the space by a countable number of curve fragment-wise charts, and the charts will have a dimension at most the Hausdorff dimension. And here a fragment-wise chart is of, well, naturally enough, defined analogously to these p-weak charts. So the differential encodes only the curve fragment-wise rate of change of the function. So no total differential can exist in this generality. And just here you measure the negligibility of the curve of fragment family by mod infinity instead of mod p. But formally it's very similar. And so this is what a fragment-wise chart is. And the result is that finite Hausdorff dimension implies that it has a fragment-wise differentiable structure. So what about the relationship with Lipschitz differentiability space? So because this thing exists for whenever the space has finite Hausdorff dimension, it exists more generally than LDS, because not all Lipschitz differentiabilities, or not all spaces with finite Hausdorff dimension are Lipschitz differentiability space, of course. That's an additional requirement. So this thing might exist even when there is no such thing. However, when they both exist, they do coincide. So this is kind of just a true, a true generalization of the LDS or Lipschitz differentiability structure to the case where there's no full differentiability. As a byproduct, so just to explain this point a little bit, as a byproduct of the construction of these charts, the proof also kind of constructs at almost every point a pointwise norm on the dual, which recovers this minimal object. And that means that when you're a Lipschitz differentiability chart, space, so you can characterize it like this. So the space is LDS if and only if, for some constant, the pointwise Lipschitz constant is bounded from above by this minimal star upper gradient. So the other inequality is always true, and this is telling you that up to a constant you have this other inequality as well. And there's a kind of a funny thing here, if you want, for those of you who know about this self-improvement of Keith-Lip condition. So we have a similar phenomenon that if you have this, and actually this C can even depend on the point, but it just must not depend on the function. So in any case, when you have this, it self-improves to an equality. So that's something about the connection with LDS. And let me very quickly run through some elements in the proof. So this monster slide here is just a vector valued version of the representation. So the point A here tells you that, so you can do this, you can find this representation that simultaneously represents the minimal weak star upper gradient of psi composed with phi for any linear combination of the phis. And this thing here is just kind of a technicality, as is this. And the proof is conceptually very simple. So you consider the following property that I call essential independence here, and it basically just telling you that, so this guy, when you fix x and vary psi, is a semi-norm, and this is just telling you that it's a norm. It may or may not be true. So, but if you can find a pair that is has maximal dimension with respect to having this property, in this sense here, well then this implies that every f has a weak differential, and the proof just goes like, you pair phi with f, now you go into Rn+1 that has higher dimensions, so cannot be essentially independent, so there must exist this vector psi, so that this quantity vanishes. And if you look at the definition, you work out the definition of what it means to be a fragment-wise differential, you just get that this vector here, sorry, there's a typo, this should be lambda. But anyway, this vector here is a differential. And then uniqueness also follows from this. So to complete the argument, if you can find maximal essentially independent guys, then they are charged, and there's this dimension bound which guarantees that they must exist. And yeah, so the proof, there are two proofs here. This is what we used, but there's also this other way of seeing it that does not use this deep theorem of De Philippis-Rindler, which I found out just recently about. And so this concludes this very quick sketch of the proof of the existence. And just as a concluding remark, so in general, Cheeger charts, oh well, this is, I guess, not wrong. So if they exist, they are the same as fragment-wise charts. But in general, these things are, again, different from the p-weak charts. There are some relationships. Yeah. And here is perhaps the way to think of these fragments-wise charts. So they the dimension is the maximal number of independent Alberti representations. So, which is the weaker notion compared to having a universal collection. So this is the difference between a fragment-wise chart and a Lipschitz differentiability chart. And as I remarked here, this is certainly possible, and we have this self-improvement inequality, and well, also we can prove something about some infinitesimal conclusions on the geometry of the space in a way using these things. And that's all I wanted to say. Thank you.
Thank you. Perhaps we have time for one question.
Yeah.
Can you comment on the relation between the fragment-wise chart discussion and Weaver derivations? I mean, there was this work by Schioppa.
Yeah, sure. So in fact, so this fragment-wise chart, or this fragment-wise differentiable structure, gives rise to this cotangent bundle, and then a tangent bundle, and sections of that bundle give you Weaver derivations. And conversely, I think any Weaver derivation is given by that. So basically, Weaver derivations are vector fields with respect to that tangent, this measurable tangent bundle. Yeah.
Okay, so our last speaker for this morning session would be Francesca Tripaldi from SNS Pisa, and she'll tell us about multicomplexes on Carnot group and the spectral sequences.
Thank you very much. I would like to thank the organizers for inviting me to speak. This is one of the few audiences for which this kind of presentation might be of some interest. So it's a nice treat for me as well. Okay, so just a quick warning. So the result itself, it's rather technical and by itself not that deep. But if you stick with it, at the end, there may be some interesting things to see. So since this is not sub-Riemannian geometry and beyond, I'm going to quickly present Carnot groups, mainly to fix the notation and present the properties that we're going to need. So we're starting with a Lie algebra. So the elements of the Lie algebras are the xi's and the thetas are the duals. So we have a grading on a Lie algebra if we have a direct sum decomposition by a finite number of subspaces that behave well with respect to the brackets. So if I have an element in Vi and I bracket it with an element in Vj, I always end up in Vi plus j. And if I have a gradient, then it means that the Lie algebra is nilpotent. So we're working with nilpotent Lie algebras. And specifically, we want a very special type of grading, which is a stratification, where the first layer bracket generates the whole Lie algebra. So these are very nice because there is a direct correspondence between the VIs, so these subspaces, and the successive steps in the lower central series. So in this case, the S that you see in the direct sum decomposition, can I point? Oh yeah, it's the nilpotency step of the Lie algebra. And we say that a group is Carnot if it's the connected, simply connected nilpotent Lie group whose Lie algebra is stratifiable. When I say Carnot, I always specify that the gradient I'm referring to is the stratification. So the easiest example and what we'll be talking about today is the first Heisenberg group. So it's a three-dimensional nilpotent Lie group, and the only non-trivial bracket relation is this one. So I have x1 bracket x2 gives x3, and a stratification is given by taking V1 to be the span of x1, x2, and then I have V2 being the span of x3. And you can see that it behaves well, and V1 bracket generates, so it's nice. So the importance of a grading is that it gives us the possibility of defining what are known as homogeneous weights, and this is through dilations. So this is a Lie algebra homomorphism. So you're scaling. Basically, the quickest way of getting this is when you have a stratification, the index of your direct sum decomposition will give you the exponent of the dilation. So for the Heisenberg group here, I'm dilating both x1 and x2 by lambda, and then to have a Lie algebra homomorphism, I need to dilate x3 by lambda squared. And the exponent or the placement in the direct sum decomposition for the xi's and their dual is going to be the weight. So theta1, we'll mostly be working with forms. So the weight of theta1 and theta2 is 1, the weight of theta3 is 2. And you extend this to these are covectors. So you can extend it in the external Lie algebra by just adding the weights, and everything works fine. So theta1 wedge theta2 has weight 2, just the same weight as theta3. This will come in handy. And the weights for theta1 wedge theta3 and theta2 theta3 is 3, 1 plus 2. And then the volume form has weight 4. So as I already mentioned, in the case of a Carnot group, the stratification gives the weight, okay? Now, this is what we're going to use later on. So it's the orthogonality by weight. So if I have forms or covectors in this case of different weight, then of course they're going to be linearly independent. And if you take an orthonormal basis, then they are orthogonal, okay? Right. So far we've been working with the Lie algebra, but we're also assuming to be working with a Lie group. So I have a left translation map. And so I can identify this, the Lie algebra with the space of left invariant vector fields. So I take them as a basis, and with if the module with coefficient in C infinity G, then I get the space of all forms, okay? So the way, and I can, in this way, I can consider the weights of forms, because I also am assuming that F, so this coefficient, it's a 0 form, so 0 forms have weight 0. So it's a nice way to extend this concept of weights to forms. Now, this is just because I'm upset about notation. So usually, when I first learned about these weights of forms, the usual notation was to mention the degree of the forms first and then the weight. However, because we're going to be using multicomplexes, the first index for us for this presentation is the weight. And the second index is linked to the degree, but it's W plus M, that is the degree of the form. So for example, if I write 2 minus 1, it's forms of weight 2, but degree 2 minus 1, 1. So it's just theta 3. And if I have omega 2, 0, then it's 2 forms, 2 plus 0 of weight 2. So it's theta 1 wedge theta 2. Okay, so there is, given this concept of weights, I can collect them. And so I can define a decrease in filtration. So I denote this by FP. So these are the forms, all the forms of weight at least P. So if I start with F0, and that's going to be from functions on, everything, then I'm going to decrease as this P increases, and I always end up with, I always obtain the zero, like the trivial space in a finite number of steps. And actually, in the case of Carnot groups, Q plus 1 will always be 0, and Q FQ is going to be non-empty. And this Q is actually the weight of the volume form. And this is worth mentioning is the same as the homogeneous dimension or the Hausdorff dimension, if you're more familiar with it. They're all the same number. And as you can see, for example, in the Heisenberg group, we had that the volume form had weight 4, which is also the Hausdorff dimension of and homogeneous dimension. Okay, so we're working with forms, which means we have an exterior differential. So we're working with the de Rham complex. So the exterior differential is the following. So you can find this definition on Wikipedia. What I would like to point out is the second addend, which is usually swept under the rug when you do courses in differential geometry, because you don't usually have a complicated Lie algebra usually. So in this construction is crucial. So as you may remember, hopefully you remember, Heisenberg had a non-trivial bracket relation. So there is going to be this addend is not always 0. Okay, so there is going to be a component here. One thing, as you can see, there is no derivative before the form. Okay, so this is what is referred to as the algebraic part of the differential, and this is the differential part. So if we use the decomposition coming from the stratification, we actually have a nice way of expressing the whole exterior differential in terms of the increase in weight. And what I mean by this, so this is going to be the algebraic part. So it acts on the left invariant with constant coefficient you can think of. And you have to believe me when I say this. If you start from a form of weight P, the algebraic part does not increase the weight. So there are two main ways of seeing this, either with a lower central series or through the dilations. But for now, you can believe me, this does not increase the weight. However, when you do the differential part, right? So you're differentiating the coefficient along XL, and then you have to wedge it with the dual of XL. So if XL belongs to the component VI, then the weight of theta L will be I. So I can decompose this differential part by the increasing weight. And this is what I mean when I write this formula like this. So I have D, which is just a sum of all these terms, and these I associate them with the increasing weight. So if I'm working, so what I'm interested in is that on Carnot groups, the increasing weight also coincides with the differential order. Okay, it's not going to be significant for this presentation, but this is a nice remark. So the fact that if I apply this to a form of weight P, I always end up with a linear, a sum of forms of weight at least P. So the crucial bit is if I start with an element in FP, so something of weight at least P, I always end up with an element in FP. Okay, and this is the the beginning of spectral sequences. Okay, so once you have this, you have what is known as a filtered cochain complex, and in this case it's of finite depth and it's stable under D. So I'm aware that this is not the standard way of picturing spectral sequences. For me, each column is the degree of the forms I'm working with, and the rows represent the weight. So going down, you're increasing the weight, and going right, you're increasing the degree. So one thing I would like to point out, I'm writing this D horizontally, but I would like you to think of this as ending up in the whole of F1. So there's going to be a part of D that stays horizontal, but also some of it will stay, which will stay in F2, but not F1, and keep going down, okay? So this is the inclusion you have to think of. So the way spectral sequences work, is that you're not computing the exterior, so the cohomology of D, whatever D you're starting with, all at once. You're shaving off parts of the D one step at a time, okay? So you're taking first what is known as the associated graded complex. So in this case, these would be the forms in FP mod of P minus 1 mod the forms in FP. So only the forms of weight P minus 1. These are all the forms of weight P, and so on. So I have a list of parallel complexes, and I'm just considering the D0, which is the differential, what I'm starting with, restricted to the quotients. And I compute the cohomology of this. Now, once I compute the cohomology of this, I no longer have the horizontal part, so I'm going to have only the parts that go down. So on the cohomology of this, which we denote as E1s now, so I'm in the first page of the spectral sequence, I only have parts of the differential that go downwards. But I'm interested in those that go +1, -1, so slope -1. I compute the cohomology of this, and then on top of those, I'm going to compute the cohomology and so on. So this is the official definition of the quotients that you see at each step of the page. So just to give an idea, EPR, so R is the page. And so I have slope minus R that I'm interested in. So, and I'm sticking to the forms of weight P. So this means that I'm considering the forms of only weight P, so at least P mod at least P plus 1. But I'm only considering on the cycles those forms whose differential has weight at least P plus R. So I go down by minus R. And that mod those that came from above R minus 1, okay? And so I'm left with the R. So I'm trying to figure out the right slope that I'm looking at now. And then the D, this curly D, is just the exterior differential restricted to the quotient. And now there is a theorem. So this is particularly nice because I'm working with a finite depth thing. So it collapses in a finite number of steps. And there is a nice theorem that states that once you've done with all the steps, this is actually the cohomology that you were looking for at the beginning, right? And you have to take the sum over all the weight, okay? So I fix the degree, and all of them, the sum, the collection of all of them will give me the cohomology. So it's a very clean theorem, actually. The problem is that if you take this as face value, it's very nice. The problem is when you want to figure out what was happening at the single steps, because there's no real indication of how to do this, especially for the differentials. I mean, the differentials is literally you have to compute these quotients and then you project them on the quotients. So, however, if you have extra structure that you can rely on, then it gets easier. So, in particular, in the case of a multi-complex, then you actually have nice formulae. So think of a multi-complex as what we were thinking when we decomposed the D. So this is what we're applying it to. So I have a bunch of maps. So I'm increasing the first index of the forms of the complex by I, and the degree is increased by I plus 1 minus I. So I'm increasing it by 1. And then for each L, these sums are 0. So if you take L equals to 0, this means that D0 squared is equal to 0. If you take L equals to 1, you have D0, D1 plus D1, D0 equals to 0, and so on. So this is a multi-complex. And by taking, so I'm taking the filtration by increasing the first index, as we did before. Yes. Yes. So if I take this filtration by increasing the first index, then I can do spectral sequences. And people, very nice people have shown that there is a way of expressing the exterior differentials in a very explicit way. So it's not done on the original quotients that we saw before. It's done through an isomorphic quotient, but these are not the same Z and B's that we were looking at before. On these, I have this explicit formula for the dr. So what I would like to point out is it's not the dr. So wait a second. So I'm starting from weight P. I need to finish at P plus R. So of course, I'm going to have a dr. So I end up at P plus R, but I'm correcting it with the di's of elements, certain elements, very specific ones that actually, so in my picture that I have in mind, if I start X here, the Z's have weight higher, so they're actually below X. And I take the di's of those. You see that the differential orders are lower than R here, okay? And the nice thing here is that there is a very concrete way of finding the Z's. We're talking quotients so up to certain choices, but it's a very nice way of finding them. Yes. Yeah. So of course, I mean, I wouldn't be talking about Carnot groups if this was not the case, but so we had the decomposition by D of the D, and this is a complex, and if I collect all the terms with the same weight, I get that these addends, and they all have different weights. And by the red remark that we had, different weights means linearly independent. So each one of them is 0. So it's a multi-complex. And this is very nice. So we can apply spectral sequences. Now, the real reason we're doing this, I mean, so far we just found a very complicated way of computing the de Rham cohomology of Rn, okay? However, there is a reason why I was looking at especially the exterior differentials of the spectral sequence, is that there is a subcomplex that can be defined on Carnot groups, which is called the Riemann complex. It's a thinner subcomplex. It computes the de Rham cohomology. So the question is, what's the relationship between the DC and these curly DRs? So what I found is that actually, so these are the Riemann forms, the space of Riemann forms in degree K. This is isomorphic to the E1 page, right? And you take the collection of over all the weights. And the DC is actually the sum of the DRs. Now this is a mistake. This should be at least a 1. Sorry. One thing, these are subspaces. these are quotients. They all act on quotients. So this would have been the end of the talk up until a couple of months ago, but now there's works by Kleiner, Müller, and Xier, and so there may be some things to think about, especially for the KMX, the final paper, because there are nice properties of these differential operators that arise. And I would say, especially when you only have one subspace here. So one example would be the Heisenberg group. So this is the 0th page. So I'm just taking the graded complex. So this is the forms of weight 0, 1, 2, 3, and 4. Okay. Now I'm taking the D on the quotients. The only non-trivial one, you have to believe me, it's this. So the D0 on theta 3 is theta minus theta 1, theta 2. So the D0 is an isomorphism here. So when you take the cohomology of that, the kernel here is 0 and the image is everything. So this row disappears. So on the first page, this is the Riemann complex. I have 0 forms, 1 forms of weight 1, 2 forms of weight 3, and the volume form. And now I'm taking the D1. So the curly D1. The curly D1 from 0 forms to 1 forms is non-trivial. However, the D1s here are both trivial. They're zero maps. And then I have a non-trivial D1 here. Okay. So what is left after? So you compute the cohomology of that, and what you're left with is constant functions here, and the only non-trivial operator that you're left with here is the D2, the curly D2. And so for this one is, yeah, it's left out. And then when basically after that, as you can see, you're done. Like you don't end up on slope -3 anywhere. So after you computed the cohomology of this D2, the sequence has collapsed. And so you're left with the cohomology of R3, sorry, which is R and all the zeros here. And this is what I wanted to say. Thank you.
Thank you. Any questions?
Is it at least approximately, I mean, should I think of the structure that you need to get from the cochain complex with a descending filtration to the multi-complex as being basically, you have these complements that basically arise from the fact that you have the stratification of the Lie algebra in the first place, right? Okay.
So, okay, so what I'm interested, so after this kind of study, what I've been interested in is how to remove as many Ds as possible. So, because in some cases you have only one weight, but most cases you have many weights. So what I'm trying to find out is a way to get rid of as many DRs as possible. So this multi-complex thing takes, I don't know, I think it helps, but yeah.
No questions? Okay. Oh.
No. Yes. So in the final paper, the pullback, the Pansel pullback of maps of regularity, at least W1P with P big enough, the pullback behaves well with respect to these DRs, the curly DRs, and not the Derham differential. So basically, so I think I haven't read like thoroughly the third one, but they cover the case of the Heisenberg group, and which in another way. So it's not this filtration, but basically what they're saying is that the Pansel pullback commutes with these curly DRs, and it's crucial that it's the curly DRs. So for example, it will commute with a curly D1 here, okay, but not the straight D1 on one forms, because this is the zero map. So it's I don't know, like this is.
Analysis together with differential forms, the Gromov complex. The right way to do it seems to be, so in the case of Heisenberg, the right way to do it seems to be. But maybe that's not a shock, right? But there's a theorem that you actually have, a Lipschitz mapping of for the planometric in Heisenberg case, then you get induced mapping of cochain complexes and use the D, not for the Gromov complex.
Yeah.
And more generally, if you have a Sobolev mapping for more general Carnot group, again, you don't have it's not you don't get a mapping of cochain complexes, but you get a mapping of this, which may be good news or bad news.
There is an isomorphism between this differential that she explained and the Riemann complex. That is.
So once you have a cochain complex with a descending filtration, there's a standard construction of a spectral sequence, right? You get a sequence.
So you get a bunch of like parallel complexes with these curly Ds. They all have the same slope.
So you get this algebraic gadget, right? A spectral sequence. It's a standard recipe for constructing it, but as Francesca was saying, maybe there's a better way of thinking about the differentials if you use the multi-complex structure, right? But you start with the existence of this spectral sequence, which is maybe a not so familiar algebraic gadget, right, from an analytical point of view. But that seems to be the natural structure when you try to bring together this the analysis with the ROM. Yeah.
So is there a Hodge theory for the Riemann complex?
For contact, yes.
Yeah. Okay.
It's so big, yeah.
No questions? Okay, if not, let's thank the speaker again.
Okay, it's time for the afternoon section, and it's my pleasure to introduce Antoine Song from Caltech. He's going to talk about hyperbolic groups and the spherical minima cycles.
Thank you for the introduction. Thank you for the invitation, and obviously it's an honor for me to be here at this event. I'm going to talk about how to construct spherical minimal cycles using some geometric group theory. So here's an introduction to my talk. The goal is to give a general construction of volume minimizing cycles in quotients of the Hilbert sphere. So I'm going to try to explain why those objects are very special and very interesting to study. And also I want to show how geometric group theory can help in constructing those volume minimizing cycles. So what we're going to do is to take a torsion-free hyperbolic group gamma, and we're going to define a corresponding spherical quotient, S infinity over gamma, and its ultra limit. And the main theorem, the vague statement of the main result is that the volume of any homonomy class in this spherical quotient is in fact realized by a volume minimizing cycle inside not the spherical quotient there, but the ultra limit. And it's going to be volume minimizing and cycles in the sense of geometric measure theory, so Ambrosio and Kirchheim. In fact, this talk is going to be an hour-long advertisement for the study of this spherical quotient, which I think is both natural and very interesting. So let's see how it goes. Right, so we're going to use the framework of integral currents, and that appeared already in the talk of Urs Lang and Stefan Wenger. So you can think of them as countable sums of Lipschitz submanifolds. There's a good notion of volume called mass. There's also a corresponding volume notion of boundary. So when a current does not have boundary, I'm going to call that a cycle. The key point is that those objects, those weak submanifolds, enjoy very good compactness and partial regularity properties, so both of them. And there's this nice theorem of Fedya and Fleming, which says the following. So if you start with any closed Riemannian manifold, and you take any homology class with integer coefficient, then first you can define the volume of this homology class. So the natural definition is you take the infimum of the volume of the cycles representing H, right? Okay, and the theorem is that there is indeed an m-dimensional cycle if H is m-dimensional. So this cycle lives in M, it represents M. The volume of T, so this cycle is equal to the volume of the homology class, and moreover, it is a mass minimizing cycle. In the usual sense that if you take any m+1 dimensional current, then the mass of T is at most the mass of this homologous current, T plus the boundary of Q, okay? So that's the basic theorem that I would like to work on, but in an infinite dimensional setting today. Is there any question on that classical result? Okay. Okay, I just repeated the statement. Any homology class is realized, the volume of any homology class is realized by a mass minimizing cycle. And what's nice about this is that a lot is known about those T's, so those minimizing cycles. This is what I was talking about, the partial regularity theory. So these T are not just some weak submanifolds. In fact, there are smooth minimal submanifolds, so vanishing mean curvature, outside of a very small subset, a codimension 2 subset of the support of T. So you can imagine that T is basically a minimal submanifold, except at some very small singular sets. So there's a lot of people here involved. And the proof of this theorem is really just a corollary of a compactness theorem of Fedya and Fleming, which says the following. So if you're given a minimizing sequence of cycles, so a sequence of cycles with mass converging to the infimum, you can always extract a subsequence converging to a cycle's infinity in the flat topology. So what does it mean to converge in the flat topology? It means that for I very large, well, you take the difference between Ci and the limit cycle. This bounds an m+1 current whose mass is converging to 0. Right, so that's the basic compactness theorem of Fedya and Fleming. So you see that using this theorem, it is very easy to construct minimizing cycles in Riemannian manifold. You just need to have non-trivial homology and you get a minimizing cycle. And what I want to discuss today is a kind of Fedya-Fleming theorem, but for infinite dimensional spherical quotients of a certain kind. Right, so since I want to talk about Hilbert manifolds, let me tell you about what's known about currents in Hilbert spaces and metric spaces. So as appeared in many talks today, there's this paper of Ambrosio and Kirchheim that extends the theory of integral currents to complete metric spaces. Okay, so that's very flexible, and it's been developed and extended by Urs Lang, Stefan Wenger, and many others. So now you can really talk about currents in complete metric spaces with, with a lot of ease. And let's see. So I'm interested in mass minimizing cycles, but let's look at the local problem somehow. So the construction of mass minimizing currents with a non-empty boundary, that's very well understood. So that's usually called the plateau problem. And say you are in a Hilbert space of, say, infinite dimension. Take a boundary. So you fix an S, which is a closed submanifold of H. Then it is by now standard that there exists a mass minimizing current T with the boundary that you fixed, which is S. And the mass of T is the infimum, quite clearly. So you see that if you want to construct a minimizing cycle, a minimizing current, even if you are in an infinite dimensional space, that's easy if you fix a boundary, because the boundary is here to anchor the sequence that you're going to take, and the limit is going to exist, and you're very happy about that. And there is a corresponding partial regularity theory, which is in its early stages, but people are optimistic that everything is going to be more or less the same as in finite dimension. I'm not a geometric measure theorist, so maybe I'm over optimistic, but what it's the current state of the art is a result of Ambrosio, Delizy, and Schmidt that says that the support here of this T is regular on an open dense subset of the support. And so you would expect that this regular part is of codimension 2, like in the finite dimensional case. That would be great. Right, so again, the full Almgren regularity theorem may hold here, but it's not yet proved. So that's the local problem, where you have a fixed boundary and you try to minimize the area of currents with this boundary. And more generally, the problem of finding mass minimizing currents with a given non-empty boundary is pretty well understood in more general metric spaces. And you have the work of many people that I'm going to maybe mention again later. But for example, currents and mass minimizing currents really provide a nice framework and tools to study isoparametric problems in metric spaces, to characterize curvature bounds, to study higher notions of higher rank hyperbolicity, and for example, show higher dimensional analogs of the Morse lemma. A lot of this appeared in the talk of Urs Lang, but here are the names: Wenger, Lipschitz, Wenger, Kleiner, Lang, Huang, Kleiner, Stadler. If I'm missing something, please let me know. Okay. Right. So this was about minimal currents with boundary, but again, I want cycles. And there, so in contrast to the finite dimensional case and to the case of minimizing cycles with non-empty boundary, it seems that there were no systematic constructions of mass minimizing cycles in, say, Hilbert manifolds, or maybe more generally non-locally compact spaces. Again, if I'm wrong, please let me know. And maybe, of course, the simplest Hilbert manifolds with, say, non-trivial homology are given by quotients of the Hilbert sphere. And so let's try to see what happens for quotients of the Hilbert sphere. I'm going to give you a very simple construction of Hilbert spherical quotient, and I'm going to try to convince you that this is a nice object. So let's start with a torsion-free countable group, non-trivial one. You can look at the unit sphere in the L2 space on gamma. So this is an infinite dimensional sphere. This group is acting on S infinity by isometries properly and freely via the regular representation. Okay. So once you have this action, what I want to do is to take the quotient. So remember that the regular representation already appeared in the talk of Ursula Hammerstadt. So it's basically action by translation by the elements of the group. This is the most obvious non-trivial representation of a given group. And you want to consider the corresponding quotient space. It's a metric space, of course, but it's also, in fact, a smooth Hilbert-Riemannian manifold. Okay, so this is somehow the star of this talk. Any questions on this definition? All right. So now, as in the finite dimensional case, maybe you have a non-trivial homology class of dimension n in this Hilbert manifold, and you want to define a notion of volume. So as usual, you're going to define the notion of volume here as, well, the infimum of the volume of cycles representing H. And this is a simple looking definition, but it has a pretty rich history. In fact, this is a slight generalization of an invariant called the spherical volume, which is due to Besson, Courtois, and Gallot. So really, for example, let's specialize to the case that Besson, Courtois, and Gallot considered. So if you look at M, a closed-oriented, negatively curved manifold, and if gamma is the fundamental group of this manifold, then you have the corresponding spherical quotient, and it has a canonical non-trivial n-dimensional homology class H. This is some elementary topology that I'm not going to explain. But so you have this distinguished homology class. You can look at the volume in that sense. Well, the volume of that homology class is exactly the so-called spherical volume of M that was defined by Besson, Courtois, and Gallot. So of course, Besson, Courtois, and Gallot didn't use currents to define that. They had another definition, but with some work, you can see that it's exactly the same number. All right. All right, so that's the definition. And historically, the spherical volume was really the key invariant in their proof, the proof of Besson, Courtois, and Gallot of the volume entropy inequality. And in fact, what they did, the core of the proof, is that they computed the exact value of that volume when M is a hyperbolic manifold, or more generally, a negatively curved locally symmetric space. So again, when M is a closed hyperbolic manifold, you have this circle quotient and a homology class. They can show that this volume is up to a constant exactly the volume of M, which is a beautiful result. And a little bit more background on the spherical volume. So the spherical volume is closely related to other invariants from topology, the simplicial volume, but also from more dynamical system theory, so the minimal entropy of M. So you can summarize that by this chain of inequality. Clearly, the spherical volume is maybe the most geometric invariant in this list. All right, so let me start talking about how to construct volume minimizing cycles. You have this group, okay? You have a homology class in the spherical quotient, and naively, you could hope that, as in the finite dimensional case, this spherical quotient contains a mass minimizing cycle that represents H. Remember, this is just the theorem of Fedor-Fleming if you are in the finite dimension. But this is never true, in fact. So whenever H is non-zero, whenever H is a non-trivial homology class, there's just no non-trivial mass minimizing cycle in this space, which is going to represent H. So that, I think, is pretty surprising the first time you see it, because this seems to be a pretty nice space, but it has no mass minimizing cycle whatsoever. So in other words, Fedor-Fleming's theorem fails. And so the result here is that it's okay, because there's no mass minimizing cycle in this original space, but you hope for, of course, for mass minimizing cycle. And so where is it? The answer is that it's going to be in the ultra limit, at least in the particular case I'm considering here. So when gamma is a torsion-free hyperbolic group. All right, so in that case, for any homology class, there is indeed a mass minimizing end cycle inside the ultra limit of this quotient. So this is a nice smooth Hilbert manifold, The ultra limit is not. It's still a quotient of the sphere, of a sphere, but it's not going to be a smooth manifold. So moreover, the mass of T is really exactly what you expect. And another key point is that, in fact, for any such T, almost all of T is contained in the smooth part of this ultra limit. Remember, the singular part is never empty. Okay, I have to mention the key points here. There are two things. So first, you need to find a cycle which is mass minimizing. So this is non-trivial. And there's a second non-trivial point, which is that you want the volume, so the mass of this cycle, to be exactly equal to what you expect, so that there's no loss of mass somehow undertaking this limit. So these are going to be the two key difficulties, and I'm going to explain more about that. Let me first remark that, all right, when the homology class is non-zero and of high dimension, so at least 2, then in fact the volume is strictly positive, okay? So I'm not constructing the empty set here. And secondly, not sure you can see it, but by Ambrosio de Lillis and Thomas Schmidt, this T is going to be a regular minimal submanifold in the smooth part of this ultra limit on a very big open set. And so on this big open set, your cycle is just going to be really a submanifold embedded isometrically by eigenfunctions of the Laplacian, which is something very special. All right. So I think from a geometric measure theoretic point of view, it's a natural problem, but maybe from a geometric point of view, it's not clear why you should care about this quotient. So let me try to explain that. Okay, first motivation, of course, from geometric measure theory. The general problem here, which is occupying a large part of geometric measure theory, is the following. So if you consider a complete metric space X and a sequence of cycles in this space representing a certain homology class, you can suppose that it's a minimizing sequence. And the general problem is what happens to Ci. And in fact, when X is a Riemannian manifold, that's fine. When X is locally compact, there are many works, say of Urs Lang, Stefan Wenger, Lipschitz. But say when X is not locally compact, it's really wide open. So that's the motivation from geometric measure theory. So let me move on to geometry here. You can think of spherical minimal cycles as some kind of special geometries. And one theorem or result in that direction is that you can show the following. So if you start with a closed hyperbolic manifold of dimension at least 3, and well, you take a minimizing sequence of cycles representing the canonical homology class, you can, so this is a minimizing cycle in the sense that you're minimizing the mass. And the claim is that Ci has to converge to something, to converge to some sense that I'm going to describe, but it has to converge to a limit, and the limit is given by the hyperbolic metric. So what's surprising here is that you start with quotient space whose definition is almost trivial. You have a homology class, a canonical homology class in that space. You take any minimizing sequence of cycles. Somehow you can cook up a limit in a reasonable sense, and this limit recovers the hyperbolic metric, which is unique. So this is mostly a theorem of Besson-Cortegallo, but to show uniqueness, somehow you need a little bit of extra work. And what I want to say is that this is true more generally for rank 1 locally symmetric spaces. So again, you have this simple-minded quotient of the sphere. This minimization procedure is going to give you limit spaces, which are giving you the locally symmetric metric. There's, by the way, a conjecture that there's a similar statement for higher rank locally symmetric spaces. I'm not going to talk at all about this conjecture, but let me quickly mention that this would imply the entropy rigidity conjecture in higher rank. It's mostly equivalent. You have the point of view of talking about the volume entropy, or this point of view of talking about minimizing sequences of cycles. These are more or less equivalent. Okay, so another thing is that when M now is any closed-oriented three-dimensional manifold, again, the limit there, the C infinity, is going to be given by a rescaling of the hyperbolic part of M. And this hyperbolic part is a finite volume hyperbolic metric that is given by the geometrization conjecture, a theorem of Perelman, of course. All right, and this is embarrassing because I don't know what happens for closed surfaces. Of course, the setup is the same for surfaces. You come up with this quotient, you have a homology class. What are the limits of minimizing sequences of cycles in that space? And well, the conjecture here is that the similar statement should hold for surfaces. So in other words, the limits that you get there for any surface, topological surface of genus at least 2, you should be able to classify them, and they should be essentially given by all the hyperbolic metrics on sigma and their limits and nothing else. No, so the S infinity gamma omega, or so let's see. So there are two spaces, right? There's this first spherical quotient S infinity over gamma, and this is really a smooth Hilbert manifold. It's just really locally isometric to the sphere, and the smoothness comes from the fact that the gamma that you take here to take the quotient is torsion free. However, I'm going to talk more about the ultra limit of that space, which is never smooth. Okay, I see your question. I see. So you can think of them as some kind of infinite version of orbifold points, but of course here the stabilizers of any singular point in this ultra limit is going to be infinite itself. And so it's a very complicated infinite dimensional orbifold points if you want. So they're what? Yes. So in the three-dimensional case, what you expect, I don't know how to prove this exactly, but what you expect is, okay, you have this spherical quotient, you have this sequence of cycles minimizing the mass, and in the limit is really living in the smooth part of the ultra limit. It's a smooth minimal submanifold given by the hyperbolic part of M. And under this limit, the non-hyperbolic part somehow disappears under this minimization procedure. Maybe it's going to be clearer in a few slides. Any other questions? So from these facts, I think it's a nice point of view to try to look at minimal cycles in Hilbert spherical quotients as a kind of GMT generalization of hyperbolic manifolds, closed manifolds, and minimal varieties in the Hilbert sphere as a kind of GMT generalization of the hyperbolic planes. So let's talk about the proof of the theorem. Remember the theorem? Maybe. Yeah, so the theorem, well, what I want to do is finding those cycles, right? So you have this ultra limit, you want to find a cycle inside this ultra limit that is both mass minimizing and has the right volume. So I'm going to give you the big tools, big principles without going to the details of the proof. The first very useful tool is a compactness theorem that's going to replace the Federer-Fleming compactness theorem, and it's a compactness theorem due to Stefan Wenger, which says the following. So if you take a sequence of cycles in this spherical quotient, and suppose that it's a minimizing sequence, then in fact, you can find an abstract Banach space B and a sequence of isometric embeddings here of each Ci in B, such that inside B, Ci converges in the flat topology to a certain cycle C infinity. So here, the limit is really a cycle in a Banach space. And this is the natural limit that you want to look at, this C infinity, okay? The terminology here is that C infinity is the intrinsic flat limit of the CJ. And you can call this infinity a spherical Plateau solution. So Plateau solution, a priori, this infinity is just some random integral current. So it's just a cycle in this abstract Banach space. It has no good regularity. You can't even compute its mass. You just know that the mass of this limit is at most the volume of H. At the end of the day, you want to show equality here, okay? So that was the compactness theorem of Wenger, and it's a lot less simple than you might think at first sight, because really it's a completely general statement where you take a sequence of bounded diameter, bounded mass cycle, you will find always a limit, which is an integral current, after taking a subsequence, of course. Any question on that compactness theorem? It's going to replace the Federer-Fleming compactness theorem. I want to give a quick definition of ultralimits for people who are not in metric geometry. So you want to define the so-called ultralimit of the spherical quotient here. What you do is you consider the set of all possible sequences of points, and you're going to quotient that by an equivalence relation. So there's a certain way of taking subsequences using something called a non-principal ultrafilter, so that for any two sequences in this big set, the distance between the two sequences is going to converge. And now what you want to do is to identify any two sequences such that this limit's distance is 0. When you take the quotient of all the possible sequences here, you get by definition, the ultralimit. And this ultralimit is still a quotient of a big Hilbert sphere, but it's not separable, and it's non-smooth. The fact that it's not smooth comes from the fact that this smooth Hilbert manifold does not have bounded geometry. So heuristically, the smooth part of this ultralimit are given by sequences of points in the original space where the injectivity radius is uniformly bounded away from 0. And on the other side, so if you have a sequence of points in that original space where the injectivity radius goes to 0, it corresponds to one point here in the ultralimit, which is a singular point. Okay. Any questions? So the point of introducing ultralimits is that, and this is an observation of Stefan Wenger, is that always the limit that you got by the compactness theorem, here, this infinity, is going to embed isometrically as a cycle in the ultralimits. So now you're in good shape because you have a cycle inside a spherical quotient. All you need to do is two things. So let me reformulate our problem. We started with this hyperbolic group. We have those cycles that minimize the mass. It converges subsequently to a cycle, which you know is in the ultralimit. And what you want to show is two things. First, you want to say something about the variational structure of infinity. You want to say it's mass minimizing. It's actually non-trivial. And secondly, you want to show volume continuity. You want to show that the volume of the limit is equal to the limit of the volumes. So here, the volume H is the limit of the masses of Ci. All right, so these are the two challenges. Right, so since you already know that you have this cycle in this ultralimit, I want to understand this ultralimit. And recall that this ultralimit is itself a certain quotient of a big Hilbert sphere. So I'm going to write this ultra limit as a big, like a Hilbert sphere, Hilbert unit sphere, mod an action of a certain group gamma omega. So this is a huge group, much bigger than gamma. And here the lambda omega is a certain orthogonal representation of gamma omega, right? You're just stating the fact that it's a spherical quotient. I'm not doing anything here. A quick remark is that in geometric group theory, taking ultra limits is something you do every day, and you use that to define asymptotic cones for some metric space. And if you have some group action on X, you can look at limit group actions on the asymptotic cone. So for those who are used to that picture, well, this is a very similar picture. And another remark, maybe to give some intuition for group theorists, is that the group here, if gamma omega, if you look at any finitely generated subgroup of gamma omega, this is a gamma limit groups in the sense of Sella. So the kind of groups that he introduced in his solution of certain problems of Tarski, which I don't understand. But the point is that this gamma omega is not something that was not studied. It's actually something that's been heavily studied, except that now what I want to know is how this is going to act on that infinite dimensional sphere, okay? So if there's no question, let me move on. Of course, you want to understand very well this ultra limit. So the study of this ultra limit is equivalent to the study of this orthogonal representation. And this orthogonal representation is, in some sense, the limit of the regular representation of gamma. I would love to know if there are references on that. I haven't been able to find any. But the main ingredient here is an old result of Gromov, Delzon, and Chainikov. So Gromov gave a certain statement that was corrected by Delzon, and Chainikov provided more details. So it's a result about finding free subgroups of hyperbolic groups. This is the main, somehow, ingredient from group theory. And it enables you to say something about the geometry of the quotient that you started with. For example, one simple, somehow corollary of all of this is a kind of Margulis type lemma. So yesterday, Sergio Zamora talked about Margulis lemmas for manifolds. Here you have something very similar, but for this quotient Hilbert manifold. Here, you can find a certain delta, which is strictly positive and depending on gamma, as it should be, such that each component of the delta thin part of this Hilbert manifold has cyclic fundamental group. Again, what it means is that if you map this fundamental group into the ambient fundamental group, the image is a cyclic fundamental group. So any question on that statement? Somehow, what I like to say is that even though this quotient is round because it's locally isometric to a sphere, because you're taking this gamma to be negatively curved, this quotient behaves a little bit like a negatively curved space. Okay, that's one particular example of what I just claimed. So what do you do with such a statement? It's a useful statement because, for example, from that, you deduce that if you have a non-trivial cycle of, say, dimension 2 or larger, so if you have a cycle in this spherical space form, it cannot be totally contained in the delta thin part of S infinity over gamma. So when it's a non-collapsing statement, basically. And whenever you have a non-trivial cycle of high dimension, it has to touch the delta thick part. And it implies something that I claimed earlier, which is that if you have a homology class of dimension 2 or larger, its volume is going to be strictly positive. And so that was known in some specific cases by combining Besson-Courtois-Gallo and Mineyev's works. All right, so that's a statement about, say, the topology of the thin part of this quotient, but I really want to study this ultra limit. And what kind of thing can you say about the geometry of the ultra limit here? And that's the main, somehow the key step of the proof, which is to show that the cycle, infinity here in the ultra limit, can be deformed to another cycle that is almost completely contained in the smooth part of the ultra limit. And that's helpful because cycles in the smooth part of this ultra limit, it's very easy to approximate them by corresponding cycles in the original space. And since you were working with cycles in the original space, now you can work out something. But yeah, here's the general property, and you don't need to know anything about integral currents. You just need to know about ultra limits. It's just a property, metric property of this ultra limit, which is that you're given any separable subset, A, in this spherical quotient, this ultra limit. Then there's a continuous family of one Lipschitz maps from A to this ultra limit, such that you start at the identity, and at the end, so you're mapping your separable subspace A to a set that only intersect the singular part of your ultra limit at a countable point. So let me repeat that. The key point is that you have a continuous family, so you have a deformation by distance non-increasing maps of the set A that you started with. I want to point out that you need A to be separable here. So, right, so any separable subspace can be deformed to something that is going to touch the singular set only at a countable set of points. So that's pretty strong. All right. So how do you use such a property? So this property is that you have nice deformations of separable subspaces of your ultra limit. Here in our situation, we can conclude because remember that we are given this cycle in this ultra limit. You want to show that the support, you want to show that it's mass minimizing. Well, what you show is that what you know is that the support of this infinity is a separable subspace. So you can use the deformation that I talked about. And you're going to deform your cycle to something, a new cycle, which is almost entirely contained in the smooth part of the ultra limit. And since this new cycle can be nicely approximated by cycles in S infinity over gamma, you can prove whatever you want because you can prove at the end of the day that this new current, but also the C infinity that you care about are all mass minimizing and they have the right volume. So they have mass equal to the volume of the homology class. And this is basically how you conclude. So any question on the principles or some details? Yeah. It's not clear at all because of the singular set. That's a good question. If there were no singular set, of course, that'd be clear because you have a continuous deformation. But here, that space has singular sets. And you need to work a little bit to make sense of the sentence that this is homologous to that. So, but in any case, the key point is really the existence of a nice family of one Lipschitz maps for any separate subspace of this ultra limit. And the intuition is that this ultra limit, again, is a quotient of Hilbert sphere by a certain orthogonal representation, right? So since it's a linear orthogonal representation, you can try to decompose this linear representation into easy to understand pieces. And once you understand those pieces, you can cook up a certain map. This is what's done here. maybe it's a bad name. It's it's really literally just a Lipschitz map, one Lipschitz map from A to the ambient space. So it starts at the identity and it moves A around to something that almost does not touch the singular set. So yeah, maybe projection is not the right word. No. So I would say what's nice is that you have a one Lipschitz map, right? All those maps are one Lipschitz, and so in the end you get another cycle. And in the proof, what goes on is that you prove that this projected cycle is really mass minimizing. And then you say, well, the first cycle that you started with is a deformation of the second cycle, so they're homologous. And you try to argue using that C infinity is itself also mass minimizing. It's a little bit like you take a curve in a plane, in a flat plane in R3. So you know that the unique plateau solution for that particular curve is going to be what's bounded in the plane. But suppose you didn't know that, and you have a random surface bounding this curve that is maybe not in the two plane, and you want to prove something. So you can use the projection on the two plane to get a new cycle, a new surface, which this time is a smooth surface bounding this curve in the plane. So you have the second one, which you know everything about, and this first one that you don't know much about, but since this map is continuous deformation and one Lipschitz, you can show that it's actually isometric, right? Something like this. All right, I'm going to end this with some comments and a question. So at the end of the day, because of the theorem, okay, you end up with a cycle which is mass minimizing in a spherical quotient. So what you can do is you can try to lift this cycle to the universal cover, right, the Hilbert sphere. And in fact, what you get is going to be a minimal variety in the sense, so a minimal current in the sense of length of the sphere outside of a very small subset. So around a very small subset, I don't know what happens, maybe the density is infinite, but you get a pretty large minimal variety of the sphere. And this suggests the following, I think, which illustrate what I really want to talk about, this connection between, you give me a group, I give you a special geometry on which it's acting on, okay? This is somehow the spirit. And in its simple form, you can try to conjecture the following. So if you take a closed negatively curved manifold M, then there should be a nice minimal variety of the unit Hilbert sphere and a corresponding isometric action of the fundamental group of M on this minimal variety, which is a geometric action, so which is proper, free, co-compact, everything you want. So since minimal varieties of S infinities have very nice properties from an analytic point of view, I think that would be an interesting fact. And moreover, we expect this sigma infinity in S infinity to be a smooth minimal surface, so a smooth minimal submanifold whenever the M that you started with is sufficiently pinched negatively curved. A comment is that you have a lot of M which are sufficiently pinched negatively curved, which are not at all locally symmetric, not topological, homeomorphic to a locally symmetric space. And that's a result of Charney-Davis plus Ontaneda. And so that means that if you plug in those M's, you should get some sigmas that are exotic or not the standard one that you could get using very easy constructions. So I think that's essentially what I wanted to talk about. Let me quickly summarize. So we started with this group, torsion-free hyperbolic. We considered this quotient, and we really cared about this ultra limit. Well, the volume of any homology class in this quotient is the mass of a mass minimizing cycle in the ultra limit. And the proof uses some one Lipschitz maps, special one Lipschitz maps of the ultra limit. And there's this conjecture that you can get minimal varieties of the Hilbert sphere from any negatively curved manifold. Okay, this is all I wanted to say today. Thank you.
Thanks. Maybe I can ask just a quick question. This lifting the sigma that is a variety, you say that it's smooth outside a discrete set of points, but because this S infinity omega is a non-separable, as I understand it, a non-separable space, it can still be uncountable, an uncountable set. Is that
right? So
the case?
In this kind of situation, you don't really care because you can take maybe a connected component, and this connected component is always living in a separable subspace. So that's cooked up in the almost in the definition of currents. So whenever you have a current, the support is
right. Yeah.
So yeah. So you can always restrict yourself to the separable unit Hilbert sphere.
Okay, and just a quick follow-up, maybe not related, I'm not sure, but so you said that it's not clear whether this proj one of C infinity is because it's that one should lie essentially inside the quotes, like, so is that homologous to the CJs for big J? Maybe this is something that
it's hard to compare them because they're really living in different spaces. The CJ, the sequence is in the original smooth manifold, but then you have this limit in an abstract sense that lives in this ultra limit. There's no natural way to relate, say, the homology class of the two.
But I mean, you could ask if they're homologous in the bigger space, like the.
But there's no canonical unique embedding of the original space in the ultra limit. You can embed it in many different ways.
See. Okay. I see. Okay. Thanks.
More questions?
Can you say anything about why minimizers never exists in
why? Okay, so one way to see that, at least in dimension one, it's easy. So if you look at when gamma is z, you can look at the corresponding quotient, and the claim is that the injectivity radius of that guy is can go to 0. So having a sequence of loops of smaller and smaller length in that space, what it corresponds to in the unit sphere of z, of L2 of z, is that you have certain functions such that when you translate them, the L2 difference between the two is arbitrarily small. But that's easy to do, right? You give me one translation, it suffices that the function is constant on a large enough interval, and then if you translate it, the difference between the two is a very small number. And in higher dimension, you have a maybe more complicated thing like this. Yeah.
Any more questions? Okay, maybe we'll leave more questions for the personal communication, and I thank the speaker again.
Thank you.
Okay, everyone, it's time for our second talk in the afternoon. So it's my pleasure to introduce Fedya Manin from University of California, Santa Barbara. He's going to talk about isoperimetric rank of a Carnot group.
Yeah, so thanks a lot to the organizers for asking me to speak, and in fact for making sure I could attend at all, because that was apparently non-trivial. And yeah, very honored to be here. I've only met Bruce a few times, but it's always been inspiring. So the slogan of what I want to talk about today is that Carnot groups have some notion of a rank, so meaning they look Euclidean up to some dimension n, and then they stop. So obviously, I appropriated this terminology from the non-positive curvature geometers, but here it's a little different because in non-positive curvature, once you're past the rank, basically you're too skinny to be Euclidean. Here, Carnot groups are going to be too fat to be Euclidean. So the question is, how do you find this n? And as often happens with nice questions that feel natural, after I started thinking about it, I found where Gromov asked it. So if you look in asymptotic invariance of infinite groups, pages 107 to 110, he discusses something very similar. So in a second, because there have been a couple Carnot talks this week, but no one has really introduced the geometry of Carnot groups. I just want to give an example, but first, like everyone else, I'm going to fix a bit of notation. So G is going to be a Carnot group. It's going to have an associated Lie algebra, funny looking G, and it has a Carnot dilation, which I'm going to call lambda t. T is the parameter, and it's going to, I'm going to sort of switch between talking about Riemannian metrics and Carnot-Carathéodory metrics. So it's going to have a left invariant Riemannian metric, which I'm going to call d-Riem, and then there's a Carnot-Carathéodory metric, which is the scaling limit. So DCC is the limit as t goes to infinity of 1 over t times, sorry, I guess I should say of x and y. So of 1 over t times the Riemannian distance between lambda t of x and lambda t of y. So maybe on the sideboard over here, I'll write down my example, and then I can refer to it throughout the talk. So unsurprisingly, it's going to be the Heisenberg group, which, right, this is the set of matrices with these entries. And if we want to understand the algebra, right, let's say I'm going to write this element as EX and EY and EZ similarly, then, right, EZ is the commutator of EX and EY. And if I take the commutator of T times EX and T times EY, I get T squared times EZ. So geometrically, right, here's my XYZ. So if I go T units this way, T units this way, T units this way, and T units this way, I end up T squared units up. So, you know, maybe to the Europeans in the audience, this is a less visceral analogy, but it's sort of like an infinite parking garage where you, in order to go up a level, you have to go all the way around. And then if you go clockwise, then you end up going down. So I've drawn this nice loop gamma here, and then the different, right? So this is in the Riemannian metric, you can get out of your car and take the stairs. It'll just be slower. But as you do this rescaling, it becomes harder and harder to take the stairs. And in the Carnot-Theodori limit, you can't move vertically at all. So you're glued to your car. So why did I draw this loop here? The point is that every surface that fills this gamma has area, and I mean Riemannian area, something like t cubed. I guess this is a lower bound. So this is a non-Euclidean filling inequality for this loop. And right, since this vertical distance is t squared, you can sort of believe that, but I'll maybe justify it slightly more later. And in fact, right, sort of the implication of this is that in Carnot-Theodori world, there are no surfaces at all. This is, in other words, it's purely too unrectifiable. Which is sort of incidental, right? You don't need to have no surfaces at all to have this non-Euclidean filling inequality, but you know, if you have this, then you know for sure. So yeah, and then more generally, you can take the nth Heisenberg group, which this is not necessarily the usual way of introducing it, but it's the central product of n copies of the usual one, meaning you take the product and you identify all the central elements. And so you can sort of imagine in, say, H5, taking this gamma and spinning it around and getting a two-sphere that's, again, going to be hard to fill. And all right. So now that I've given this introduction, I can tell you some possible notions of rank. The first one is actually not isoparametric, or at least not obviously so. But it's maybe the most natural. It just says that every continuous map from an n-disk to your group can be C0 approximated by maps that are Lipschitz in the Carnot-Theodori metric. Oh, yeah. I'm defining rank as less than or equal to, sorry, greater than or equal to n. Yeah. Yeah, thanks. and all the rest are going to start with for all k less than n, right? So one is there is a C such that every L Lipschitz map from a K-sphere to G, and this can be with either metric, has a CL Lipschitz extension to dk plus 1. And this is a notion that I think Robert Young first called Lipschitz n-1 connected. And then, right, this one, well, first of all, it's easy to see that it implies the first one, but also maybe the benefit of it is that you can measure its failure in a quantitative way. Right, so you can define a Lipschitz filling function which is the soup over L Lipschitz maps from SK to G. And now I really have to use the Riemannian metric of the inf of the Lipschitz constant of all extensions to the disk, right? So if this is, right, this condition is saying that this function is linear, and then you can measure how nonlinear it is. So for example, for the nth Heisenberg group, the nth Lipschitz filling function is at least n plus 2 over n plus 1, sorry, L to the n plus 2 over n plus 1. And I believe there's some work of Wenger and Young that shows that this is close to the real value. So maybe let me give 2 prime, which is similar, but sort of even less quantitative. So for all k less than n, every Lipschitz map from, now I have to use the Carnot-Theodori metric because this is always true in the Riemannian metric, has a Lipschitz extension. To the k plus 1 disk, and there's an implication this way. I'm pretty sure there's also an implication this way, but I haven't written down the proof yet, so I'm going to hedge my bets. And then, since this is taking a lot of time, I won't spell out what what 3 and 4 are, but for those who know, right, you could have a Euclidean Dane function, you could have a Euclidean homological Dane function. And there are implications going this way. I think this one is due to Basso, Wenger, and Young. But it's sort of not clear whether there are implications going backwards. Yeah. It's less than or equal for sure. So let me get to that. But they are definitely not the same. Yeah, so I can at the end, hopefully I'll have time to get to more examples. But yeah, so let me start with some things that are known. Yeah, so one specific example is jet spaces, right? The largest abelian subgroup of JKRN has rank much more than n, but the rank in this sense is n. Yeah, so here's something that's known. That's due to Gromov in his Carnot-Theodori paper, right? Suppose that G is a step 2 Carnot group. So the Lie algebra decomposes as a direct sum where the right V2 is the center, and then this is the bottom layer. So if you divide out by V2, you get something abelian. And suppose there's an abelian subspace in the bottom layer, so n-dimensional abelian subalgebra, such that if you take the linear map from V1 to here, where you take a vector in here and you look at its pairings with everything in S, this is surjective, then G has rank at least n. So this is what's known. This is how you get the lower bound for the Heisenberg group. So this condition is a little bit mysterious, but basically, right, you take this one n-dimensional abelian subalgebra, and somehow the existence of this surjective mapping tells you that there are a lot of abelian subalgebras, and actually there's enough that you have micro flexibility, so you can sort of take Lipschitz maps and extend them, and then to get this approximation property, right, you end up taking smooth pieces and sort of folding them like this. And yeah, so this implies that H2n plus 1 has rank at least n, and it's a theorem of Burio from 97 that this is sharp. So he showed this, that this curve is hard to fill. And so let me very quickly sketch the proof. So we already saw some cohomology of Carnot groups earlier today. For me, it's going to be much simpler. I'm really just looking at the invariant differential forms on G and taking their cohomology. So this is a finite dimensional algebra, right? It's the exterior algebra on the dual of the Lie algebra with a differential, which is in some sense dual to the Lie bracket. And in fact, right, there's a theorem of Nomizu that says that for a nilpotent Lie group, if it has a lattice, then it's the same as the cohomology of that lattice, the group cohomology. So for example, for the Heisenberg group, right, this is generated by these 2n plus 1 forms. And where the differentials are all 0, except for the differential of dz, which is the symplectic form. And so the fact is that our cycle, any filling of our cycle pairs non-trivially with this n plus 1 form. And then if you use the Carnot dilation, right, these all get multiplied by t. This gets multiplied by t squared. And so, so when scaling by t, the volume of the cycle scales by t to the n, and the volume of the filling scales by t to the n plus 2. So let me now, so this is as much as I'm going to do of this. And now let me turn this into a definition. So G is n formal if the cohomology in degrees at most n is actually all coming from stuff that gets scaled by t. So In other words, the map from the cohomology of the abelianization to the cohomology of G is surjective up to degree n. And then I'm going to give another definition. G is n scalable if it's n formal, and there's two equivalent conditions. One is cohomological. So for all cohomology classes in degree at most n, there's a map from the cohomology of G to forms on Rk, which sends alpha to something non-zero. And this is equivalent to saying that all the homology groups through dimension n are spanned by abelian horizontal subgroups. So and now I can state a theorem, which I guess I'm taking credit for, although it's really, I had to do almost zero work for this. So suppose that you know that the rank of G is at least n. So if G is not n plus 1 formal, then the Lipschitz filling function is at least L to the n plus 2 over n plus 1. The homological filling function is at least v to the n plus 2 over n. And then if G is n plus 1 formal, but not n plus 1 scalable, then the Lipschitz filling function is at least L log L to the alpha, where alpha is some positive constant depending on the homology ring, cohomology ring, and then the homological filling function, all we know that is that it grows strictly faster than Euclidean. So, and then basically the proof is, first you, right, this all involves having some favorite cohomology class. So you find a cycle whose every filling pairs with that cohomology class. And then in this case, you apply Burillo's argument. In this case, you apply an argument from a paper of mine with Sasha Berdnikov and Larry Guth. And in this case, you apply an argument of Wenger. And then to find the cycle, well, it's right. So you, yeah, let me not say that. Let me use my last negative however many minutes to say a couple of examples. So I already talked about Heisenberg groups. The quaternionic and octonionic Heisenberg groups also have rank n. So so I should say it's maybe not totally clear from the way I stated this, but this gives an upper bound on the rank of any Carnot group, which may or may not be sharp. But it's sharp in the case of these two groups. So this one, you use the non-formal criterion, and this one you use the non-scalable criterion. And these were both already known. So this is due to Pité, and this is due to probably Moritz-Gruber. And then there's the jet space groups, and then the lower bound in both these cases is using Gromov's theorem. So here, these jet space groups, the lower bound is due to Wenger and Young. The upper bound is due to Rigo and Wenger. And then, so this is also, you can apply the non-formal clause here. And then there's Wenger's examples of groups with Dane function strictly more than n squared, and at most v squared log v. So this is another non-scalable example. The only new example where it's sharp that I've been able to come up with is you take the octonionic Heisenberg group and you mod out by one central element, which is not supernatural, but it's another non-scalable example. And then I've been talking to Robert about a bunch of examples where we don't really know what happens, and these include free products of, central products of free step 2 nilpotent groups and sort of generic step 2 groups. So I'll stop there. Thank you.
We will have time for a quick question.
Did I understand correctly that you're saying that you find a representative of the Lie algebra homology for the filling?
So for the filling, yeah, so both of these conditions say there's some element of the Lie algebra cohomology that if you find a cycle that pairs with it, then that's going to not scale in a Euclidean way.
Okay.
And then you have to find the cycle, but that's not too hard.
Okay. Thank you.
Gromov's theorem, that's for step 2. So everything that you did afterwards, is that still step 2?
No.
Oh, that's
so yeah, my theorem works for any Carnot group.
Okay. But then my argument is just like a higher dimension analog that you mentioned there in the end, that you would do a similar argument for the super Euclidean.
Yeah, so it's the same argument in any dimension, right? You have something that can't be you have a cohomology class that doesn't pair with anything abelian, so then you know that.
Thanks.
Okay, we'll probably leave more questions after the talk. So let's thank the speaker again.
So we'll consider Gromov-Hausdorff limits. Say the Ricci curvature is bounded below by that of hyperbolic space, and the non-collapsing condition is 2. The volume of the unit ball at the points pi has a definite positive lower bound V. And I want to discuss some structural results. The newest are joint with Aaron Neighbor and Wenshui Zhang. The reference is Annals 2021, and as you can see, it's a long paper, very technical, so I won't say anything about the details of the new results, just a little descriptive, but I want to mostly provide the context, meaning the history, going back, say, to the work with Toby Colding. So here's the main result I want to talk about today. HK denotes Hausdorff measure, and it says that such a limit space has a decomposition, which I'll write as S epsilon, and union the complement R epsilon. R epsilon is the regular set. S is closed. Sorry, the epsilon regular set. I'll say what it is on the next slide. S epsilon is closed, n minus 2 rectifiable, and there's a definite bound on the volume, say intersected with the unit ball of the type written in 3 with the sharp exponent r squared. So that's the volume of the tube of radius r, and in particular the Hausdorff measure of S epsilon intersected with the unit ball also has a definite bound. The epsilon regular set is theta of epsilon by Hölder equivalent to a smooth Riemannian manifold, where the limit as epsilon goes to 0 is 1. So some definitions: the epsilon regular set, that's the set of points at which every tangent cone is epsilon close to Rn in the scaled Gromov-Hausdorff sense, meaning on every scale the distance is less than epsilon r. And S epsilon, the epsilon singular set, so that gets bigger when epsilon gets smaller, that's the complement of R epsilon. And just for our purposes, a metric measure space with measure Hausdorff k-dimensional measures, k rectifiable, if there exists a countable collection of measurable sets, AI, such that for all AI is by Lipschitz to a positive measure subset of RK, and the measure of the complement is 0. So in the work with Toby Colding, we showed in particular that the singular set, which can be described as the union over epsilon of these S epsilons, that's the set where some tangent cone is not Rn, that has dimension in the sense of Hausdorff dimension at most n minus 2. And easy two-dimensional examples show that this is sharp. And we used the methodology going back to the 60s maybe early 70s, DeGiorgi, Federer, Fleming, and Almgren introduced it in the context of minimal varieties. However, its use in Riemannian geometry required new techniques, basically because there isn't a background metric. So the methodology involves filtration, which I've written below. If you want an example to think of in your head, it could be, you could think of them anyway as the closed skeleta of simplicial complex. Now we talked about tangent cones, and I remind you that a tangent cone, say at a point X, is a rescaled Gromov-Hausdorff, pointed Gromov-Hausdorff limit. And the existence of such in our context follows from Gromov, pointed Gromov compactness. Now, non-collapsing implies, can be shown to imply that every tangent cone is a metric cone. So I'll remind you what that means below. And then SK is the set of points at which no tangent cone splits off isometrically a k+1 dimensional Euclidean factor. And corresponding to what was shown in the earlier classical work in the context of minimal varieties, the basic point is that the dimension, Hausdorff dimension of SK is at most K. So again, think of the skeleton of a simplicial complex. So the Hausdorff dimension inequality is proved by iterated blow-up arguments. So these are arguments by contradiction. If the desired conclusion fails, then it's shown to fail for a tangent cone. And this is helpful since tangent cones have special structure. They exhibit radial invariance, and in our case, actually, they have non-negative Ricci curvature in a generalized sense, in the sense of being Gromov-Hausdorff limits with the lower bound on Ricci going to 0. So here's the definition of a metric cone. The distance between 2 points in polar coordinates is given by the law of cosines. The cross-section y is a length space, and in our case, it's connected with diameter at most pi. So note, this is consistent with what you would expect by viewing Euclidean space as the cone on the unit sphere. And you can think of diameter less than pi as coming from Meyer's theorem, because the cross-section of the cone should have Ricci bounded below by plus and minus 1. Okay. Now, the iterated blow-ups that works as follows. Each point of the cone, except perhaps the vertex, if the vertex happens to be unique, lies on a ray. So after blow-up, if we take such a point, then the ray becomes a line. So now we've done a second blow-up, once to pass to the cone, and then we blow up again. And in fact, we'll say more about this later, the blown up cone actually then would split off that line as an isometric factor. So then we could reiterate this argument, and after k+1 blow-ups, we get always blowing up at a point that doesn't lie on the Euclidean factor, all of whose points consist of vertices. We get something which splits off our k+1, such a cone. Now, by a density argument, this is the whole point, and this argument isn't difficult. As indicated before, the blow-ups also satisfy this SK is non-empty if the original limit space did. So this gives a contradiction. Okay, so that's how these iterated blowups go, which is the tangent, the classical methodology as implemented in our case. Now, let epsilon, let Mn sub h denote the n-dimensional simply connected space of constant curvature h, and let P underline denote any point in that space. And we denote by the script V sub h of R, the ratio of the volume of a ball in our manifold, whose Ricci is bounded below by n-1 h, divided by the corresponding volume in the model space. And the crucial properties for us of this volume ratio are that it's monotone decreasing function of R, it's a priori bounded below, that's the non-collapsing condition, the bounded above would hold in general, by bounded above by 1, and it's coercive, which is the name I'm giving to what's also called almost rigidity. So I'll remind you now what these conditions mean. So monotonicity, that's just the Bishop-Gromov inequality. And the a priori boundedness, as I said, it's always bounded above, but it's also bounded below because of the non-collapsing condition that we've assumed. So now the coercivity, that's concerned with the almost equality case in Bishop-Gromov. And here I've written it down formally that if over these values of R, the volume ratio hardly changes at all. So that's the almost equality case. Then the claim is that this ball would be Gromov-Hausdorff close to a ball in a cone centered at the vertex. And so we could summarize that by saying almost volume cones, or maybe since we're still talking about annuli, almost volume annuli are almost metric annuli. And almost volume cones are almost metric cones. So this was not easy to prove. It's not just a matter of using the ODE arguments, which you could use for the equality case, but it's much stronger. Okay, so now what does that tell us in our context? So from now on, let's go back to the normalization. The model space has curvature -1. And for example, let's call 2 to the -j a scale. So then we could use anything other than 2 if it were convenient. So now by Markov's inequality, there are infinitely many scales, but right, because we're going down, say, from 1 to a half to a quarter and so on. But according to what we just said, this volume cone condition, almost volume cone condition, can, for a given epsilon, can be violated by at most n of epsilon scales. And therefore, on all other scales, what you see is very close to, let's say, a ball in some metric cone. The scales, particular set of scales on which it's violated will depend on the point a priori. But we have to deal with that later. Nonetheless, at this point, almost all scales, it looks like a ball in a cone. I sometimes remark when giving this talk that actually this could have been guessed a lot earlier from the, so in other words, if you look at these under a microscope, almost all the time, what you'll see is a cone. This could have been guessed earlier without the tools to prove it, just from the equality case, which is really an ODE argument. But I don't think it was. So here's a remark for what's coming in the talk, that we had an effective estimate on the number of bad scales, and we used it to pass the conclusion from the approximating manifolds to the limit spaces. But then the application in the work with Toby up to that point was that tangent cones are metric cones, which is a statement about the infinite, infinitesimal scale, not on a definite scale. So there's also a side remark that in the work with Toby, we also gave another almost rigidity theorem, namely a quantitative version of the splitting theorem. And this applies to possibly collapsed tangent cones in particular, because they are limits with the lower bound on Ricci going to 0, so they have non-negative Ricci in a generalized sense. And the original splitting theorem with Gromov was for non-negative Ricci in the smooth case. So, okay. So now, let me recall how we obtain lower bounds on the codimension of singular sets. So this is the same idea that was used in the earlier work on minimal varieties, but this is the implementation in our context. And the results on the lower bounds on the codimension, the method is always the same, depending on what we're talking about. Ricci, minimal varieties, harmonic maps, etc. But the actual result will depend on the particular, let's say, equation, although lower bound on Ricci so far is an inequality that we're talking about. And so what you have to do is, if you know that you're talking about cones, then you can say, hopefully, what the possibilities are, namely, what are the cones that split off a definite factor. So in our case, if we want to show that the singular set is actually the set in the filtration corresponding to n-2, what we have to show is Sn-1 with Sn-2 deleted is empty. Now, what would the possibilities be if it weren't empty? Well, what you can see is if it splits off Rn-1, the only possibilities, the cross-section has to be connected. So it's either Rn, which is not singular, or n-1 cross R plus, in other words, a half space. Now, a half space, of course, is a perfectly good cone, but what we showed is, and this is the typical thing you have to show, is that it's not a blown up limit space. So, okay. Maybe one more remark here is, if you think about it, to understand why it's not a blown up limit space, in the relevant case, if it's, think of it as a limit of pointed spaces, then the base point would have to be on the boundary. And that kind of looks wrong, because the boundary is a boundary point, whereas in the manifolds of which it's a limit, the boundary is a distance, let's say 1, if we're talking about unit balls. So it looks wrong, and you can make that into a proof actually in various different ways. So the key technique that was used in this work, I'll call it elliptic regularization. And that means specifically approximation by distance functions. So U think of as a coordinate function in a space that splits off, let's say, a line, or the bold-faced R squared, let's say in Rn, or more generally a cone, the Laplacian of that function would be 2n. So say in Euclidean space Rn, the Laplacian of R squared is 2n, and the Laplacian of a coordinate function is 0. It's harmonic. It also has the property, of course, crucially, that the norm of the gradient is identically equal to constant, say equal to 1. And actually, it's a fundamental point that this is an intrinsic description of linear functions in Rn as harmonic functions whose gradient pointwise norm is constant. So in this argument, we use, of course, so it's a regularization. So we want to estimate distance functions. We take these model functions, so to speak, maybe with the same boundary values on a ball, and then we can apply Bachner's formula to estimate Hessians and the Cheng-Yao gradient estimate to estimate gradients. So again, if we were in the ideal case of a product with a line, then the coordinate function is harmonic and the norm of its gradient is identically 1. And as I already said, in a cone, we would have the Laplacian of the distance squared from the vertex is 2n. So there are certain tools which are necessary to implement these ideas. So first of all, so we want to know that the regularization and the distance function, corresponding distance function, are close. So that's like that it is a regularization, that is assuming the geometric hypothesis, say close to a volume cone or close to a splitting. And for that, we use Bachner type arguments to estimate the Hessian. But this required having a good cutoff function, which was non-trivial to construct. The construction that we gave used quantitative Laplacian comparison. One can also regularize a more naive distance function by heat flow. So the main point is one needed a cutoff function with a bound, pointwise bound on the Laplacian, an absolute value. And then once one has the closeness in the integral sense to really get the corresponding estimates on the distance function, which was the goal, we needed a refined version of the Poincare inequality, which we call the segment inequality. And that's what's used to passing the estimates on the regularized functions finally to the corresponding estimates on distance functions. So there's also the case of two-sided bounds. So this is more like an equation. You could think of Einstein manifolds where you would have equality if you wish, but it works the same way except for a little loss of regularity in the case of a two-sided bound. And then, as we showed in work with Aaron Neighbor from 2015, the codimension of the singular set, which is now going to be closed, previously it wasn't necessarily closed, is codimension 4, the codimension 4 conjecture. And this had been conjectured since the early 90s, I would say, by Nakajima, Anderson, and Tien independently. It appears in the write-up of Anderson's ICM talk. And the key point, which was understood from the work of Toby and myself, although it wasn't understood at all how to do it, was that you have to show that you can reduce to codimension 3. Going from 3 to 4, you can do by topological argument, which is not so difficult, showing that the relevant projective space doesn't, using the fact that it doesn't bound. So you had to rule out the product of I think I meant to write the cone on S1 with on a circumference. Yeah, so in 14 it should be the cone on a circle of length strictly less than circumference strictly less than 2 pi. And what we showed, which was the crucial point, it was known all along that this was the crucial point since the work with Toby, but it wasn't known how to do it, that this cone is not a blown up limit space under the above conditions. So the point now already from the work with Aaron in 2012, this was earlier work, and this was the break with tradition, that rather than proving Hausdorff codimension estimates, let's say, which again refer to effectively the infinitesimal scale, we used effective estimates to get results on a fixed scale. This was for the first time. And so, for example, putting together the later result on the codimension 4 conjecture with those techniques, in the case of a two-sided bound, we could get an estimate on the volume of tubes around the singular set, which would be closed in this case, which makes it look almost as if it were a codimension 4 smooth submanifold of a manifold. So the estimate is 15, and what you would like is an exponent 4, but what we could prove at that point is 4 minus eta for any positive eta, but with a constant in front of it that blows up as eta goes to 0. So we almost got, at that point, almost in quotes, what you would think of as the what would be the sharp result. But of course, getting rid of the eta is a kind of borderline thing to try to do, and it required entirely new techniques after these from 2012 and then 2015 in that particular application. Now, a crucial point also that we did at that time was to show that outside of the tube of radius r, we actually have a pointwise bound on the sectional curvature, again with the annoying eta, any eta less than 0, and a constant that blows up in front of it as eta goes to 0. So these type of results were really new in partial regularity, and we showed, partly joint with Bob Hasselhofer and Daniele Valtorta, that you could use the same techniques and get corresponding results for minimal varieties, harmonic maps, mean curvature flow, harmonic map flow, critical sets of elliptic equations, etc. And other people, of course, took this up and proved results in other contexts as well. So in the background, at least as far as I was concerned, was earlier work on what I call quantitative differentiation. And this was formalized in the work with Bruce and Asaf Naor in 2009. And then I wrote a kind of abstract or generalized version in a paper in 2012 in CPAM. But what I think is somewhat striking is the work with Bruce and Asaf was in a totally different context. It was about Lipschitz maps from the Heisenberg group to the infinitesimal target L1, where it's particularly non-trivial to prove by Lipschitz non-embedding results because you can't use differentiation theory in the usual sense. It required a new differentiation theory and these quantitative differentiation ideas. So what I'm trying to emphasize is maps from the Heisenberg group to the target big L1 looks on the face of it rather different from what I've been talking about up to this point. So these kind of quantitative differentiation ideas, the first such result that's normally quoted, and I think it's fair to say, was in work of Doron-Soro. Then there was work of Peter Jones, including on the analyst traveling salesman problem, David Sems and Ribe. But I want to say it's an interesting point for me in mathematical sociology that the full extent of the applicability of the underlying idea was missed. And in my opinion, if it had been part of a standard education, something you can certainly do to an honors analysis in an honors analysis course for undergraduates, or at least maybe I should say in times past, one was used to being able to do it. If the simplest case, which deals with Lipschitz functions on the line, had been part of a standard education, then these very tough guys like DeGiorgi, Federer, Fleming, and Holmgren might well have done this quantitative case decades before the work of Aaron and myself. So some of the new techniques that we used in that work with Aaron were a quantitative version of the filtration, quantitative cone splitting, which I'll say something about momentarily, energy decomposition, a covering argument, and novel epsilon regularity theorem. So I'll indicate something about what these refer to now. So the quantitative, it's usually called a stratification, but in my opinion, it's better to use the word filtration. So probably I wasn't quite consistent. So let's call a ball K epsilon symmetric if there exists a cone which splits off RK, and in the scaled Gromov-Hausdorff sense, scale invariant Gromov-Hausdorff sense, the Gromov-Hausdorff distance between your ball and the ball in the cone is less than epsilon r. So now we, for arbitrary positive epsilon and r, and k greater than or equal to 0, we define the quantitative counterpart of the previous filtration or stratification, depending on your taste, to be the set of points where from, say, scale 1 down to r equals 1 to s equals 1 to s equals r, for no s is k plus 1 epsilon symmetric. And then it's easy to see but fundamental nonetheless, that the thing I previously called S epsilon, which is the intersection over all R of these SK epsilon R's, is S epsilon, and the kth SK in the filtration is the union over epsilon, positive epsilon, of these SK epsilons. So it's a very fruitful quantitative generalization. and the point is to do something with it. So here's another point that we used. Its non-quantitative version was used in, say, the context of minimal services and harmonic maps. There are some very good notes by Leon Simon. You can find them in write-ups of the Park City, the appropriate Park City conference, and I'll refer to it as cone splitting. So what it says is the following. So let's understand it as cones in our in the context we've been using, although the context there was I forget, probably harmonic maps, maybe minimal services. It's the same in all these cases. So what it is suppose I have a cone, and it's a cone in two different ways. So by that we mean that there are points, say x1 and x2, and maps, isometries to two, in principle, different cones, which carry xi into the vertex yi star of said cone. So we assume that the points are different. X1 is not x2. And then, in fact, what you show without too much difficulty, but it's a very fundamental point, that if something is a cone in two different ways, meaning two different points can act as vertices, then in fact they lie on a line, and the line splits off isometrically. So we call this cone splitting. And you can think, if you wish, of the example of, I mean, Rn is a cone on any point. So let's think of the points coordinate 1 along the x-axis and -1, and look at the difference in the distance functions from those 2 points. And then what you see is that the difference is the linear function x1. To get x1, you would divide the right-hand side by 4. So cone splitting was an effective version of this. So what that means is if we have k points and they're sufficiently separated, but inside the ball that we're looking at, but since we wanted quantitative, and before we were talking about 2 distinct points, we assume a definite separation between any pair of these points. And then we have the not cones, but close to cones in the Gromov-Hausdorff sense, sufficiently close. Then we consider the regularized distance functions. So that is, we look at distance squared from the ith point and take the harmonic function, not harmonic, but solving the Poisson equation with right-hand side 2n as its regularization. So the difference between 2 of these is harmonic, and after suitable normalization of the differences, we get these what we call epsilon Gromov-Hausdorff splitting functions, which are shown to give rise to an epsilon r Gromov-Hausdorff equivalence with some cone that splits off the factor rk. So that's an indication of the idea. And now the volume bound in theorem 4, meaning the volume bound on a tube, it's weaker because of the eta, the annoying eta, than what was in theorem 1, which didn't have an eta. It would have been just r n minus k. So this goes back to the paper with Aaron from 2012, and I'll briefly indicate where the proof comes from and the reason with that technology why you couldn't get rid of the eta. So the point is, it uses the effective bound on the number of bad scales. So remember, I made there's someone at my door, but I'll attempt to ignore it. I made a remark about the effective bound, but the earlier use only at the infinitesimal level. So one point was what we call the energy decomposition. And what this means in words is at every point in this set that we're trying to estimate the volume of a tube around this set, at every point we have good and bad scales. Now, the problem is, so there are only a definite number of bad scales. That's what we said earlier. That came from the almost volume cone as almost metric cone. But the particular collection will depend on the point. And therefore, you have to do something to make them cooperate if you want to implement this quantitative cone splitting. However, the key thing to realize is there's a definite bound polynomial on the in the sense of the key point on the transparency on the number of collections, because if we didn't have a definite bound on the number of bad scales, and we imagine that the possibilities could vary from point to point, then there would be exponentially or even more possibilities, because any sub-collection of scales could be bad scales. But when we know that there are only a definite number, that gives us a big improvement on the bound for the number of different collections. If we sort points put them in the same collection, if they have exactly the same number of good and bad scales, particular bad scales. So that's the key point. And therefore, what follows is we can look at the collections of which the number goes to infinity, but much more slowly than if we didn't have this bound on the number of bad scales. We can look at each collection individually, get an estimate for that, and then multiply by the number of scales, which is growing as we consider down to a scale that's going to zero, but much more slowly than if we didn't. It's going to infinity, but much more slowly than if we didn't have such a bound. So then we just have to prove an estimate for a particular C. And now the point is that we're going to do a covering argument of a rather elementary type. Namely, we think of the set we're trying to cover, SK epsilon, in a unit ball, as a kind of generalized Cantor set. And so we cover by balls, and then each ball we cover by, say, balls of half the size, and so on. The whole point of this sorting is that when we have the same good and bad scales, then on the good scales, the different approximate cones cooperate with one another in the sense of this quantitative cone splitting that was explained earlier. And okay, so what that will mean is that on a good scale, we have this approximate splitting of this set we're trying to cover. It's very close to a Euclidean k-dimensional factor. And so when we cover, in effect, we just covering by a number of balls, which is as if we were in RK. On the bad scales, we have at most a definite number. So there, it's kind of harmless to use a covering by balls as if we were in Rn, because since there's a definite bound on the number of bad scales, it's just going to put a constant in front of our estimate. And that's the constant that depends on eta. And so that's roughly how that argument goes. And it's written carefully here, but I won't read on the slide. The basic idea is what I said. So to repeat, on the bad scales where we don't have closeness to the appropriate number of cones, we just cover by balls of half the size, of which there'll be roughly 2 to the n. And we're covering a ball of radius 2 to the minus j by balls of radius 2 to the minus j plus 1. And that's how you complete the proof. So this was in the argument in the paper with Aaron from 2012. Now we get the corresponding result for the Einstein case, let's say, where we have two-sided bounds, and then we get the corresponding result. We use the epsilon regularity theorem that if it splits off our n minus 1, or rather if it's close to, sufficiently close to it, or n minus 3, rather, if it's sufficiently close to such a ball in the scaled sense, then it's actually regular. And that's proved by the same kind of compactness contradiction argument that was pioneered by Mike Anderson. And in that way, we complete the proof in that case. And in all the other cases, it works in the same way. So the point about the work from 2012 is anywhere you had a bound on the Hausdorff codimension, a lower bound established by the described methodology, you could turn it into something effective. So what's the source of the annoying eta? I mean, of course, if you're a little bit experienced, you know that getting rid of the eta is a borderline result, and such things are notoriously difficult. So there are really 2 points. One is the energy decomposition, where we did this sorting into points with the same good and bad scales. And the other is a factor which arises from recovering of balls by balls of, say, half the size. Now, in the second one that's not so essential, because the difficulty came from overlaps when we recovered, but you could do something like using Voronoi cells, sometimes called crisp cubes, if I'm using the terminology correctly. And then 2 is not really the essential difficulty. But the energy decomposition into sorting things by good and bad scales, which was very pleasing when we thought of it, that has to be replaced by something else to get the borderline result. Okay, so just to think of it at the formal level, what we have is, suppose we had a series of positive terms and a bound on the sum. So first of all, this implies the nth term goes to 0, but we can say something more quantitative just by using Markov's inequality, otherwise known as the pigeonhole principle in this case. And we, for any b positive, we would get a definite bound on the number of terms of size at least b. And in fact, the ratio, this C would go to 0 as B goes to 0. But of course, this is still weaker than what we're looking for. I mean, that is to say, we haven't used all the information if we just think of that simple sort of toy argument. So to prove theorem 1, somehow in the geometric situations or analytic situations, you have to make full use of the fact that the sum of the terms in the series is bounded by C. So this is possible in these contexts, but it's not easy. So there was a second breakthrough in this quantitative partial regularity theory, and was due to initially Neighbor and Valtorta, who in particular had a new Reifenberg slash rectifiability theorem, and the hypotheses were much weaker than any previous one. But among the techniques were a highly non-trivial induction argument, a highly non-trivial covering argument. But the crucial thing conceptually was a theory of neck regions, meaning you really wanted to study the problematic regions where you were in the transition between the regular and singular parts. So you had to have a new theory of that, which is what was done. And this immediately became the gold standard in partial regularity theory, to the extent that some of the people who came afterwards weren't even aware of the earlier work with Aaron. So they proved mass-bound and rectifiability analogous to what I had stated in Theorem 1, and the context was minimal varieties and harmonic maps for the work with Aaron and Valtorta. And then with Aaron and Wenshui Zhang, they implemented these techniques in the Ricci context, but with a two-sided bound. Recall, Theorem 1 assumed just a lower bound. So in particular, they proved rectifiability of the singular set and the sharp bound on the volume of a tube with no eta, namely singular set as codimension 4. So you would want for the volume of a tube, the power r to the 4th, which we had actually done in the 2015 paper with Aaron in dimension 4, but the general case is much harder. And also, similarly, Neighbor and Zhang proved the sharp bound, namely with the exponent 2, not a smaller one, this a priori bound, L2 bound on the Riemannian curvature tensor on its norm in the non-collapsed case, which I think is just a terrific result. So again, we had shown this in the 4-dimensional case with Aaron, with a bound, and in general, but with the bound that L2 minus eta, with the constant blowing up as eta goes to 0. And to show the subtlety that these new techniques could handle in the harmonic map case, the sharp result, which they were able to prove, Neighbor and Valtorta, is a weak L3 bound, which means that the maximal function behaves as if you really had an L3 bound. But on the other hand, it's known that L3 is false. So we had shown LP for all P less than 3, but this borderline result, you can see how delicate it is, because L3 is actually false, and yet you can get the sharp result, weak L3. So now I'll say one more thing about the case of Ricci bounded below, non-collapsed Ricci bounded below, that I had in Theorem 1. And that is that the paper, remember, was 125 pages long. So it requires completely new estimates from the Neighbor and Jean paper, since the estimates that were crucial in that paper needn't hold if we just have a lower bound on Ricci. Now, of course, this revolutionary theory of neck decompositions still plays a role. The Reifenberg argument has to be replaced by a more canonical one using harmonic splitting functions, which I've given an indication of how that goes, but one needs really sharp control. And so then there's this sharp cone splitting theorem and a sharpening of the transformation theorem, which was in the 2015 paper with Aaron on the codimension 4 paper. So, okay, I'll stop here.